Yeah, it's 220.
Whoever's here.
Not cool. Or we require if you leave me at that time, I will go faster. Yes. Justin. Say something.
We always have no not efficient, not efficient.
People have raises in our group. And you know, exactly. And the other thing, Bob has answered for me. It's not very good.
Yeah.
So it. It's not business. We were following these. This is all you know. Right? Okay. Yeah. No, I was trying to say what was it? Oh. Yeah, we break your associations. So it's embarrassing.
Hmm? Yeah. So good.
Welcome back, everyone. We've all had a nice lunch break. Thanks for joining us. This session is going to be on plant formation and discs. So our first speaker is Andres Izquierdo, who's going to tell us about exooma and kinematics of discs.
Good. Thank you. Yeah, it's not a pleasure for me here this time on my first year second fellow at the University of Florida. I graduated from the Light University in December last year. And today I would like to discuss about how to use this schematic information to try and further location of massive planets embedded in disks. In particular, in the context of ExoAlma, which is a large program by ALMA. But before going into the details of the details of the disk kinematics, I would like to just highlight very quickly what I really sensitive to, like in this parameter space, what I'm sensitive to when we use parameters. So, for example, here, the only thing that I would like to note is that we're pretty much limited to tiny planets that are located in large radius separations from the star. And still, even though we're not able to access the entire planet population parameters here, these little codes can actually, fully very easily solve the codes here on the other side of the parameters. So understanding the characteristics of these young mass plants is really crucial, and actually confirming whether they are there or not, because they can influence the disk evolution and therefore also influence things like the diversity of physical and chemical parameters that will end up making up the fully formed exoplanetary systems. But one of the things that we are having here is that the majority of those color points in this portion of the planet are actually inferred based on the presence of those solid structures. We know from theory that planet disk interactions can actually steer things like gaps and rings, or things like spirals, or asymmetries as well in the millimeter and also in the definition. But we also know that all the physical mechanisms creating higher instabilities, gravitational instabilities, things like winds, energy winds, or evaporative winds, and leads to very similar to the surface and thus continue. So locally, ALMA also gives us access to the bulk of the gas material through molecular line observations. Okay. And the cool thing about molecules is that depending on their chemical properties and the way they respond to the radiation field, and also things like optical depths, they are usually very highly certified entities. So for example, say that you take molecular line observations of CO isotopic emission, but here we see optical thickness of those tracers. Alright. That's here we see optical thickness of those tracers, and therefore we will be located in the uppermost layers of the disk in this atmosphere. And then as you go to less dense tracers like 13 CO or C18, you will start probing layers that are closer to the disk. This allows you to do like a three-dimensional scan or tomography of the protoplanetary disk. And we also have kinematical information on these molecular observations. So we have unlocked this new dimension here, which is the velocity dimension, just to illustrate what the typical cinematics look like for at least like MWC for 80 as observed in 0 and 6. So we have a subset of channels, tracing material that's moving away from the observer, especially inside of this. Then we also have a subset of channels expressing the fluid inside of this. Typical spacing 0.2 kilometers per second. But with that one, we actually, illusion images have twice as narrow channels. We have 100 meters per second resolution. The other thing I wanted to point out is that now that we have access to the gases, we also need to understand what's the typical kinematical signatures in pure like planets. Right? So say if the planet is massive enough, for example, and if the viscosity conditions allow it, the planet itself is going to be able to carve a gap at its rate of rotation. This gap is just a pressure combination to which the gas is also responding, so it's an additional central force. Therefore, you're using as a little velocity flows, but also at the same time because of the interaction with things like viscous torques in this atmosphere, you can also use meridian flows of material when you're filling the gap open by the planets. On the other hand, we also expect to find localized velocity perturbations around the immediate vicinity of the planet, like this kind of Doppler eclipse, because of the gravitational pull of the objects, and also varying the scale perturbations like spirals. Spiral density waves, which also have affected by the velocity fields. Increased velocity dispersions are also quite common according to the theory because of the interaction with the gravitational torques in this medium induced by the planets. On the other hand, viscous torques in this atmosphere. Those are result velocity flows, for example, like turbulence, to which we also send. However, we do not have direct access to these velocity signatures. What we observe is again density channels projected per velocity for frequency, in this space. And what we see, according to also the theory, but this is also been observed in multiple sources, is this kind of king-like structure, this kind of thunderbolt-shaped patterns, indicating there is something perturbing the channel at that particular location. Okay, so part of my job in the previous, also 2 or 3 years, has been to actually try to quantify the underlying velocity perturbations leading to these kind of kings or wiggles in the channels. Also try to use this information to try to pinpoint the location of the planets with high precision. So here is where we'll introduce X1. Basically, what we're trying to do with X1 is to decide what kinematical analysis in a systematic way, in a statistical and cost manner. Of course, X1 is just a combination of many different efforts from many people. But today I would like to basically focus on the contribution to these projects. So X1 was designed as a personalized funding campaign in the sub-millimeter ALMA. And also it was designed to understand and to resolve the dynamical structure and physical structure of those planet-forming environments. To do that in a homogeneous way, we targeted 15 of the largest and brightest sources in nearby carbon locations, plus 2 disks. with sizes ranging from 200 a year to 1,000 a year in 3 different lines, LCO, WCO, and CS in Band 7, that's about 340 gigahertz. And indeed, that's at a very high spectral length that's waiting for maintaining sensitivities that require a lot of telescope time, more than 180 hours telescope time. So this is just a view of the different sources that we have in Alma, as observed in LCO taking this. And the beam size here is the same for all of them, so you measure and the sources are typically located at a distance of between 150 to 200 parsecs, so it's similar distances for all of the sources. So kind of really judged more or less by differences in these little circles, which ones are the largest and the smallest. So CP tau is one of the smallest ones, about 200 a year. But then we also have these peaks like 30,015, about 1,000 a year, like I said, tau is similar size. You cannot really judge just by looking at this simple map that many of those disks are actually not necessarily accessing this very kind of insert sort of structures, like this part here, the CP tau. There is little, parts, so perhaps localized perturbations in this or B in some channels and stuff like that. So already from simple maps, we were kind of seeing that our sources were perhaps higher sort of structure. So these little movies that I'm showing here are just to highlight that things are also quite common apparently across radial and perhaps even very extent over disks. As you can see, there are disks with different inclinations. We focus on this one here, which is here in page one, but you can see the many vehicles that it has multiple velocity channels. Okay, here I'm giving the same channel spacing as I told you, 41 kilometers per second resolution. And then we also have more compliant sources like this one here. I believe this one is like 8,015, or actually HD422. Where we see also, we start to see the backside of the emissions. You can see we have front side and back side. And this really is particularly linked to the pre-sub region, in this case, CO. And something we're also taking into account with our models, the ones that I'm going to show. There's another high in the top, so like C758, which exhibits system spores or apps. Not observations. So someone can keep the presence of solid structures in possibly kinematics, but also perhaps in the image. So how do we extract this information? How do we quantify or see underlying velocity information as opposed to these field channels? Well, we do as a collaboration is that we're using this minor code, which I developed at the beginning of my PhD. And what this minor does is something very simple. It just assumes that the input data channels are smooth and learning, utilizing different ingredients, such as this vertical structure, which is key. We're using different molecular traces, and as I told you before, different molecular traces are actually coming from different types. So the midway, it's important to take that into account. We are also accounting for discrimination, stellar masses, and also for time properties, relative conservation. So once we have this smooth and vectorial model, what we do is that we start making comparisons. And we can collapse this into moment maps and produce large scale analysis to try and understand what's the temperature structure of our disks. For example, all these products here infer the elevation of gas caps through the presence of pressure modulations. Perhaps they're talking about turbulence in the disk. Also infer where or characterizes spirals, rings, parallels, or structures. And something that I would like to show you later is the clustering algorithms that we utilize to look for plants in these disks. Okay. So this is just an example for the NHFP, the NHFP44B. Still time I have left? Wait. So here we have data channels, model channels, and testing. Okay. And then we also have more inclined sources like HTTP422, where we have the same story. You know where the model is actually accounting for those front sides and back sides of the population. This is quite important because remember one of the key things that we want to do is to characterize moment maps. We want to do this kind of sizing. You know, the typical calculations in years like that is around 200 meters per second. So we also require to understand how moment maps are, calculated and collapse. It's really vital to do that So that's what we're going to do with the data. You do analyze the data already accounting for the vertical structure extracted by the model, but you can start computing this kind of gradient profiles, taking density, language, and data curves, all of which would tell you something different about the physical and dynamical structure of our business. Okay. So the other thing that we can do is again start making comparisons with our this mind model, smooth declaring model. If we do take in this case we take the velocity maps that we calculated both for the data and for the model, we can start looking into deviations from the federal notation. Finally, we are able to quantify what's the level of deviations we have in the sources and start categorize things. For example, CDI, you remember that there were hints of diagram structures. Actually, there's probably something connected to this beautiful spiral-like filament of structure. There is also spiralizing, for example, in the CZ58, bring structures in other sources, localized structures in other disks. So there's really a myriad of different signatures that are probably responding to different mechanisms as well. And now here is where we use small scale analysis to look for planets, localized perturbations in the velocities. But we're doing also with textual analysis, we can characterize line with increments. No atoms. Line with increments are highly sensitive to the elevation of planets. So we're using clustering analysis to validate these techniques, calculate what's the typical precision of these detection techniques. It's pretty high precision. And we apply this to our data, HT30, and this is where we think there is a planet, there is a localized object on this side, there is highly clustered signals on the other side. This is how these potential planet candidates look like with respect to satellite spirals and millimeter pulse creation. And then we have the other sources, but I'm gonna leave there just to was just to mention that this is just what was a very simple picture of the whole story. Yeah, I'll leave it here. Thank you very much for your attention.
Thank you so much. We have time for very questions. Yes.
Can you constrain the mass of the mold? Can you determine one mass with a maximum mass?
Yeah, so we're currently doing that with program modeling. So since now we can quantify the level of the amplitude, so we can actually, run higher simulations and try to, increase masses until we get the same level of perturbations we are observing. So yeah, you can do that.
Thank you so much.
Thank you.
Next up, we have Cheng John Jang, who's going to tell us about shadows in transition disks.
Okay, thank you. Hello, everyone. I'm Shanja. I just started my position at Columbia University, and I graduated this summer at the nearby city, Las Vegas, at UNLV. Today, I'd like to share with you my recent work on 3D radiation hydro simulations of shadows on transition disks. So Andreas has introduced you a very wonderful, beautiful ARMA large program, ARMA, and you know that ARMA is a very powerful tool to study protoplanetary disks. But I want to show you another mode of observations, which is from this near-infrared scatter light images. In this kind of observations, we also accumulated around 100 protoplanetary disks, and we also see many substructures, and they can be different than those observed from ARMA, even in the same disk. For example, you see rings, whatever. You see rings, you see spirals, and these spirals occur more often than what you see in ARMA observations. And additionally, you see in some cases there are shadows. We have broad shadows and narrow shadows. For the broad shadows, the shadows can be very wide, and they are one-sided. Namely, half of the disk is inside of the shadow, and the other half is out of the shadow. And for the narrow shadow, they are quite narrow, and they're coming in pairs. Basically, they're separating apart 180 degrees. And you see shadow, there must be something blocking the light. A common explanation for this kind of shadow is misaligned inner disk. And this inner disk is often unresolved, but you can use the shadow's morphology to infer the inclination of the inner disk. If the inner disk is just mildly misaligned with the outer disk, like this plot, it will cast a very wide shadow, and half of the disk will be in the shadow. If this inner disk is almost perpendicular to the outer disk, only 2 parts of the disk will be in shadow, and they are separating around the 180 degrees. So this is not new. There are many papers talking about this, and people not only try to identify the inclination of the inner disk, people also do observe this in a yearly basis, so that you can see the change of the shadow, so you can infer the precession rate of the inner disk. Those studies are very good, but I would argue that there's not just this radiant transfer effect. I want to argue that today that the shadow not only is a consequence of this geometry effect, it also changed the dynamics of the disk. So what we want to study the dynamics and the radiant transfer together, and we need to use radiation hydrocode. And I want to introduce a very good radiation hydrocode, the Athena++ and radiation module, because this one is really good compared to other codes on the market. It can work both at optically thin and thick regimes, and what it makes it very unique is that you can pass this shadow and thin test. Thin test is very simple physical problem, but it's really hard to realize in this kind of radiation hydro simulation. You just propagate 2 beams into different directions, and they will merge cross each other at some point. For this our skin, they will propagate in their original direction after they passing by. So this is quite physical. But if you're using another kind of treatment that needs a closure, after they merge together, they will propagate in the vertical direction, which is not physical, but it is just unavoidable due to the matter. So the reason that we think that the shadow can lead to dynamical effect is quite natural, because when, like here, we are in Pasadena, when you are exposed directly by the sun, you feel hotter. And when like today, it's not sunny, you feel not that warm. So you can imagine across the shadow, there can be a temperature gradient. And temperature gradient can lead to the pressure gradient. And pressure gradient is a driving force. And if you have a shadow there, they will be providing a constant driving force that leads to some dynamical effect. So we use a very simple geometric to study the effects of the shadow onto the transition disk. The disk is truncated, so there's a cavity, and in the beginning of the simulation, there's nothing, there's no shadow. But then we introduce a shadow in these 2 directions. So this simulates the inner disk that is perpendicular to the outer disk. As the simulation starts, you will see that the temperature in these 2 directions becomes lower because they're in shadow. And then you see the spirals are launched and connected to the inner cavity. As the simulation evolves, there are some vortices forming in the spirals that can disturb the pattern. And at a later time of the simulation, there's a giant vortex forming at the cavity edge due to the Rossby wave instability, because we have very low viscosity here. And these spirals launched by the shadow can also lead to accretion. You may already see that in the previous movie that there are more and more material coming into the inner disk. And this is the case. In the beginning of the simulation, the density in the cavity is very low, it's 10 to the negative 5. But after 500,000 years, the density becomes much higher. So that means the spirals can lead to accretion. And if you measure the effective renal stress and calculate this alpha accretion rate, it can be as high as 10 to the negative 2 in the inner disk. So that is quite strong accretion. We can also compare our simulation with observations. So this is a famous disk with shadows and also spirals, HD142527. You see one shadows here, the other shadows there, and there are spirals seemingly launched by the shadows. In our simulation, we put them in graded transfer code, and we also see there are shadows and spirals launched by the shadow. So this is really good. But what I have been talking about are mainly focusing on the mid plane or the R5 plane of the disk. Because I use the 3D red hydro simulation, we would also like to see what happened in the vertical direction. And this is actually comes to very basic graduate students problem. If you want to calculate the vertical structure of a global planetary disk, or you want to calculate the scale height of the Earth's atmosphere, you would want to balance the vertical gravity with the pressure gradient. And if you balance these two terms, you would work out the vertical structure of the disk. And it is exponential to some Gaussian. But this is the case for asymmetric disk. If you now, the temperature changes as a function of the azimuth, then inside the shadow, because you have lower temperature, your pressure will be lower, so your pressure gradient will be lower. So this pressure gradient cannot support the gravity perfectly. The acceleration is pointing downwards. And on the contrary, if you are outside the shadow, your pressure is higher, so this pressure gradient will become higher, and the acceleration will be pointing upwards. So this effectively gives you a vertical motion of the disk. And if you work out the momentum equation, you will figure out there's an extra stress term, this partial rho phi, rho v phi dt, partial rho phi term that can perfectly balance the leftover between these two terms. And this introduces you the azimuthal variation of Bz. If I play the movie, and this is the vertical slice of the disk, and it's not changing your time, it's just scanning through the azimuthal direction, you will see that the disk moves upwards and downwards in a period. And this has strong implication to observations as well, because in recent observations, like Andreas introduced the axial AMA observations, we can see the velocity of the disk in very high resolution. So we measure the velocity, three components of the velocity of our simulations at the emission surface of our bidirectional disk. And you can see this velocity per azimuthal variation, redshifted blue-shifted pattern across the disk. And the magnitude can be at least 0.1 kilometer per second. And this can well be observed in recent AMA observations, like axial AMA. So I guess I will just conclude here. First, shadows can act as a driving force and launch spirals. And the spirals leads to accretion, and they can feel the material inside the cavity. And a spiral launched by the shadows can naturally explain the coexistence of the shadows and spirals in near-infrared scatter light images. On the vertical direction of the disk, this imbalance between the vertical gravity and the pressure gradients makes the disk to move in the vertical direction. And we can possibly, very likely, to observe this vertical motion in not in the current AMA observations, such as axial AMA. Thank you for your attention, and I would be happy to take some questions.
Any questions? You know, I have one to start. What causes this misalignment between the inner and the outer disk?
Yes, that's a good question. Probably planets. So The misalignment means the perturber probably somewhere here, and the perturber also needs to be misaligned with the outer disk. Either a very massive planet or a binary can do this. And there are also other mechanisms. There are like 3 alternatives, but we hope it would be a planet.
Any other?
Do you think there could be ways of distinguishing planet-driven spiders? It's kind of shadow-driven spiders, and looking at different state types to see how it's very clever and very emotion spiders types in the next lane. That's something that we will investigate further to see if they are distinguishable.
Yeah, I think.
Can you repeat the question?
Yes, the question was: can we distinguish between the planet-launched spiral and shadow-launched spiral? My answer for now is that I don't know much because I only run one situation, one setup, and I need to cover a more parameter space to fully compare with the spirals launched by planets. But in theory, after the spiral is launched, it doesn't care what launches a spiral. So I think for planets, you still need to find this very localized perturbation that can be trying to pinpoint the planet.
Any final questions? Okay, as we get our next speaker set up, I have one last thing. Do we think there's ever a case where you really have an inner disk completely perpendicular?
Yeah, I think completely perpendicular might be difficult, but all those narrow shadows, they have the neutral inclination between, say, like 70 degree to 90 degree. So you can treat them as almost completely perpendicular.
Thank you so much.
Thank you.
Our next speaker is Fong Long, who's going to tell us about an interesting carbon-rich disk with JWS.
Thanks. So hi everyone, my name is Fong Long. I'm a second fellow based at Arizona. This actually is my last symposium. So first of all, thank you everyone here, and thank you for the leads for the program and all my fellow peers here for the wonderful time. Actually, we'll miss all of you. So today I'm going to discuss some new interesting results from James Webb. In fact, in my proposal that I submitted for this program, I aimed at making connection to James Webb, but at that time, it was just about to launch. So I'm really happy that I can now really talk about this topic. So we know that the planetary systems are quite diverse, and this diversity has to be related to their forming environment, those gas-rich and dusty disks around young stars. So the mass, size of those disks, its chemistry, structure are all important factors that can determine what types of plants can form in those systems. So understanding those key properties and its time evolution is really crucial to give us a complete view of planet formation. So in the last 2 symposiums, I focused on the armor view of disks. So we looked at those detailed structure in the outer part of the disk and tried hard to find the young planets there, even though we are not very successful for now. But now with the infinite capability of James Webb, we are able to dive into the very inner region of those disks and to review the rich molecular content in those areas. So in this talk, I will try to briefly touch on the complex interplay between the outer disk structure and also the inner disk chemistry by focusing on a very special type of disk. So why are they special? They are special because they are very old. They are like tens of million years. So by counting the disk fraction in star clusters of different ages, we know that the typical disk lifetime is only a few million years. If we're looking at the gas component for accretion, that would be even shorter timescale. So those timescales are very important for planet formation, right? Because you need those materials to be there to form planets. And for our recent observations, we seem to suggest that, okay, planets will need to form very quickly in the first million year. So it was a really big surprise when we realized that there is a bunch of disks which are very old, as tens of million years, but still show accretion, which means that there's still gas remaining in the system after tens of million years, which is crazy. So maybe in some cases, we don't need to rush build those planets. So for now, this type of system are quite small numbers, about 10. So here I'm just showing one example. This is a young system, not young anymore, belong to the 40 million year old Carina Young moving group. Its optical spectrum shows clear evidence of accretion, and the lack of lithium absorption is a strong indicating that this is quite old as 40 million years. So those type of disks are first identified through its very strong infrared axis, which are quite comparable to many young disks in of a few million years. But at the same time, such high level of infrared axis is also comparable to a special type of debris disks, those so-called extreme debris disks, which have experienced some very recent giant collision similar to the events that made our moon. And so given their comparable ages, it's likely that those old guys, old accreting systems are just analogs to those extreme debris disks. And the accreting gas may come in from the collision events of some volatile-rich bodies. That's one possibility. And then we notice that those old accreting systems are all around late-type stars. So for for very low-mass stars, because of their weaker radiation field, their disks can indeed live longer. So another possibility is that they are indeed primordial disks that happen to persist much longer than we usually expected. So how can we distinguish the two scenarios? This is actually the main goal of my James Webb Cycle 2 program. So with Mirror MIS, we're going to explore the inner disk gas and dust properties and try to find out what's going on with them. So from the gas side, we know that from speeder time, young disks often show very strong molecular emission in the mid-infrared wavelengths, including like water emission of organics like CH2 and HCN. So if we can detecting those characteristic lines, that may point to a primordial region. And then on the other hand, high energy impact will produce SiO gas. And also their dust property will be very different. We will expect to see more abundant silica emission and also more iron-rich grains. So by looking at the dust and gas properties in those systems, we will see what's going on with them. So just last month, we finally got our full data. So here I'm just showing an initial overview of our sample with mirror spectrum. So the first impression is that, okay, good. We are just seeing primordial disk because we see so abundant molecular line emission. So some of those isolated bright lines are emission from molecular hydrogen, which have been detected in all but one of our disks. And then around the 40 micron range, we see very prominent emission from hydrocarbon organics. So even though the lines are very obvious in our spectrum, but this is only because of James Webb, we can now detect them. So in the following, I want to zoom into one disk and to see what their key properties look like. Okay, so in order to identify lines, we have to first remove the background continuum. In this process, we notice that there are two small bumps around 7 and 14 micron, which also associated with some molecular lines. We then realized that, okay, those actually can be produced by gas emission if they are very optically thick, like a pseudo continuum. This already suggests that we have very high abundance of hydrocarbons in those disks. And then we further identified 10 additional hydrocarbon molecules in the system, even including benzene emissions, very bright in the system, like six carbon species there. On the other hand, for oxygen-bearing molecules, CO2 is likely the only species detected. And for water, which is very weak and barely identified in this target. So given that we have such a large number of detection, many regions have overlapping lines. If we want to find in other fainter emissions, we have to come up with a model that can well produce those known species. This is what we did. For example, I'm showing a best fit that model in this busy 14 micron range. And we saw we're able to find another line, which is the neon gas at 12.8 micron. So neon is a super volatile species. So its presence highly suggests that we are really seeing primordial gas that persists in the disk for tens of million years, which is crazy. So next, let's see how the property of this old guy compares with many other young systems. So here I group the targets with mid-infrared spectrum by their host star property. And our old system is marked by this, this star symbol here. And so on the left, I'm comparing the line emission from water versus C2H2 emission. Those are the two most important carbon and oxygen carriers. We see that M-star disks have generally fainter emission. This can be understood as the temperature difference, right? So a disk around a more massive star will be warmer, which can lead to brighter line emission. And then on the right-hand side, I update the y-axis to reflect the line ratio of the two. You can see that for M-star disks, even though with much fainter line emission, we have much higher line ratio. This is pointing to a more enhanced carbon chemistry in those M-star disks. We do notice that there are two outliers, which are quite young, but show very similar property to sunlight stars. So I will come back to that very shortly. Okay, so several chemical models predict that if you increase your gas-phase ratio from solar value to near 1 or above, you will see a huge increase in the hydrocarbon column because any remaining carbon finds a hydrogen-formed hydrocarbons. So we can then use those model grids to estimate what is the level of C2 ratio in our disks. This is what we found. So most of the disks around low mass stars have super solar C2 ratio. And especially for those older systems, they have generally much higher C2 ratio, which means that they are very carbon rich. Well, in the younger systems, we can see a wide range of ratio. And in particular, these water-rich stars, which are much similar to sunlight stars, have typical solar value. So we have tried hard to understand, okay, what might be causing this difference? And we then realized that they have very different denser disks as seen by ARMA. So here I'm showing the ARMA image for only 4 disks, which have recent GEMSWAP data. You can see that for the 3 carbon-rich targets, they have very faint millimeter emission, even including 2 non-detections. Where on the other hand, this oxygen-rich target, very bright emission, and they also have gap rings in outer part. So we know that those icy pebbles in outer disk, which emit at millimeter, they are subject to radial inward drift. Once they go across the water flow line, they will sublimate and enrich the water content in the inner disk. So we speculate that, okay, in this oxygen-rich target, it's likely due to the presence of those gap rings that slow down the radial transport of those pebbles. So there will be continuous supply of water to the inner region as long as you have a dust disk in the outer part. So then how can we apply this idea to the majority of disks? So we can imagine 2 scenarios. On the one hand, there is the one I just introduced, those dust pebble drift, they bring in water inside, so it becomes more oxygen rich. And then on the other hand, you also have accretion process that can transport carbon-rich gas from the surface inward. So comparing the 2 processes, drift happens much faster. So the computation of the 2 then involves the system age. So you can see that for a smooth disk where drift happens very quickly, we expect that the C2 ratio to first drop because of your icy pebble drift in, your ice sublimation bringing oxygen. When that was suspended, then you get an increased C2 ratio because of the accretion gas coming through. Remember that most of those M-star disks have very faint emitter emission, which means that we have used up all their pebbles. So they have already passed this oxygen-rich period and now become more carbon-rich. Well, if you do have some substructures in the disk which slow down this process, so you will get a much prolonged period of this oxygen-rich part. But eventually it will be carbon-rich because you will one day use up all your isotopes there. So I think this scenario quite explains well our finding of those very old disks with very high CO2 ratio, because that's the point, you use up everything and you remain carbon-rich in the end. So to summarize, our GenSwap data showed that some disks can indeed live very long, and their gas are mostly hydrocarbon rich. So I think this result had wide implications in our understanding of plant formation and evolution. On one hand, remember this is a gas that will supply the growth of planets there. So those planets may have a primordial atmosphere which are hydrocarbon rich. Can you imagine how this might affect your further atmospheric evolution and even the detectability of those rocky planets? Are all interesting for now. And also probably those are progenitors for TRAPPIST-1-like systems. So the long presence of those gas may just help the planet migration and rearrange them into resonant chains. So I think they are very unique and interesting systems. Thank you.
Thank you so much. Oh, multiple. Okay.
That was a fascinating talk. I was wondering if I understand the implication here is that you're saying that the reason that the TRAPPIST-1 system may be an oddball among the other UCVs that have been surveyed for similar planetary systems that come up empty is because of the early disk evolution, which is also rare when you're looking at these longer-lived disks. Is that correct?
I think that would be my interpretation, because those disks are the rarity, they are not the majority of systems. Not most of them can live such long. So in fact, I will only find one versus one. I guess that be a very interesting coincidence there. Yeah.
Yes.
So this is, at least I find it very, very interesting. How do you reconcile this with the mass from the mine survey and what detecting water in the inner parts of this, in some of these? Is it because the host start is different? Is that age thing? How do you reconcile those?
Yeah, so he's asking, there are some disks have water detection. Yeah, definitely. So for most M-star disks, we don't have much water. But if you're looking at some stars, there's tons of water. On one hand, there's a temperature difference because water actually provides high temperature. So if you don't see them, it may not mean they're not there. It just means they have very cold, they're not easily emitted to be observable. But the ratio of the carbon species to water is the absolute difference between the two types of stars.
Awesome. I'm so sorry we're going to have to move on, but let's thank Fong again.
Thanks.
We'll move from carbon to sulfur chemistry. You're from Charles.
All right. Hello, everybody. My name is Charles. I'm a second-year Sagan Fellow at the University of Virginia, and today I'm going to be telling you about sulfur in protoplanetary. All right, so I have to thank all the previous speakers for introducing protoplanetary disks and why we should care about planet formation. Hopefully you all do care. The one thing that I just want to stress here is that protoplanetary disks are really the last stage when we have substantial reservoirs of primordial molecular gas. And so they're the ideal places to understand the chemical conditions in which planets are forming. And in many of these systems, planet formation is well underway. And so that really we're looking at the environments where planets are directly assembling. And so I'll just jump right into what I want to talk about today. And so here are the census of molecules that have been observed and detected in protoplanetary disks to date. Perhaps the infrared portion of this is a little out of date now already because of JWST. But you can see here each column represents a different type of molecules. There are neutrals, CO isotopologues, nitrogen, oxygen, hydrocarbons, and then lastly, sulfur-bearing molecules, which is in this column here. And what you might notice is there's relatively few sulfur-bearing molecules that have been detected in disks so far. And what this means is we have a wide degree of outstanding questions, not limited to this list here, which is what is the actual underlying sulfur reservoir in our disks? Why have we detected so few of them? The chemistry that we do observe, is it set by inheritance? Is it just coming from the molecular cloud that the disk formed from? Or are there active in situ processes that are changing this sulfur reservoir? And lastly, and perhaps most interestingly, how does the ongoing planet formation that I just mentioned actually affect the chemistry that we observe? And if you look at this list here of the sulfur molecules that have been detected in disks, you might think, oh, this is actually a fair amount. But if you go ahead and cross off those that have only been observed in maybe 2 or a few systems, we're really left with only a handful of molecules, basically 3, CS, H2CS, and SO. So these are the 3 molecules that I'm going to be talking about today. CS is the simplest, just 2 atoms. It's bright. It's the most often detected in disks. H2CS, we're now beginning to detect more. It's a little weaker, but it's showing somewhat unexpectedly high abundance in disks, saying that we might have a little more organic gas phase sulfur than we initially expected. And then SO, which has become a particularly exciting molecule. It's the only oxygen species that we can now reliably detect. But it often occurs in interesting systems, those that are young, that have active accretion, large-scale structures, dynamic things going on. And so to just show you what this typically looks like, if you get a nice CS detection, it looks very much like a disk. It is highly spatially resolved. It is bright. The main problem here is that we often just do one line at a time. So our excitation, what the actual gas temperature, density, and so forth, those are a bit limited by single line observations. H2CS, on the other hand, as you can see here, that looks a little less like a disk, a little more like a blob. The signal to noise is lower. The lines are inherently weaker. And so we don't have as many detections, and they are not as well spatially resolved. SO, on the other hand, is much more complicated. That doesn't look like a disk at all, right? The red region there is showing where the dust would be in this source. And so there is still an open and fundamental question about what is SO actually tracing? Is it the hot gas? Is it shocks, outflows? What is going on at SO? So today, I just want to talk about 2 projects that I've been working on over this last year, and just try to convince you that sulfur-bearing molecules might be a nice way to actually probe into planet formation going on in these disks. So the first project, I'll talk about using sulfur molecules to map the disk conditions. And then the second case, if I have time, we'll mention an example where we can actually use sulfur-bearing molecules to perhaps find planets themselves. So let's get started. So the first disk I want to introduce you to is HD 16296. It has this really beautiful multi-ring structure. It's relatively nearby and modestly inclined with respect to us. The main thing I want you to take away from this is there's evidence of multiple Jupiter mass planets in this disk. Particularly, I want to just focus on the one candidate that exists here. It's about a Jupiter mass at around 83 AU or so. And this is a very well-studied disk. It's been observed many, many times with ALMA, and you can see the large amount of archival data here that I've compiled. But it turns out that there's not many observations of sulfur-bearing molecules in this disk to date. And to put that in context, here I will show you a gallery that I will slowly populate. Here is the dust, and here is the one line of one sulfur molecule that we had in 2021. It's just tracing the cool gas. It's a low J line of CS. But if we take all of that archival data and go through it, we get something like this. Now we have essentially all of the CS lines that are observable by ALMA. We can go from the cool ones to the lukewarm ones up to the hot tracing lines as we go from progressive J transition here. And they're all at high resolution too. They're at around 0.2 to 0.4 arc seconds, or at the distance of this source, a few tens of AU. But if we keep digging into the archival data, we see more. We see the isotopologues as well. That is, instead of seeing the 32 sulfur, the most common sulfur isotopologue, we see the 34 as well. We also detect some lines of H2CS. So now we have an entire family of sulfur-bearing molecules in this disk going from one line to nearly 10. And I should note that this is the first detection of the isotopologue of H2CS, 34 sulfur. And this will be led by a PhD student out of the University of Tokyo. Yoshihiro Yamato is going to put together the discovery paper for this. But what it lets us do is actually get a really good handle on the excitation of the sulfur gas. So this is a rotational diagram for CS. So this is just a way to fit for the temperature and column density of your molecule. The main point I want you to take away is the more orange points you see here, the better your fit is. And to compare it to something state of the art several years ago, we had 3 points for CS, and now we have 7 in this disk. So really putting this together, we tighten our error bars, and we can get a really good idea of what's going on, what's the temperature, what's the density of our CS gas. But we can do some perhaps more exciting things, and that's because we have very high angular resolution. We have at least 4 CS lines going from J equals 8 to 7 to the 2 to 1 line that are at around 35 AU resolution. And so we can convolve them all together, put them on a same spatial scale here, and actually look for some morphological trends. And in fact, we do see some. So if you notice, this is going in terms of from the bottom, this is the upper state energy of the line, so tracing cooler gas, up to the top, tracing hotter gas. Another thing that's varying across these lines is your critical density. So you're starting from lines that have low critical densities to high critical densities. And what you might notice from just looking at the morphology of these lines is that when you're at low J, low critical densities, you just have one giant wide ring. But by the time you're up to the top of this plot, now you have 2 very distinct and well-separated rings. So your morphology is changing going across these different lines. And this is something you'd only know if you actually put all of these lines together. So what we think we're actually seeing here is subthermal excitation happening in that region with the actual gap. So that's what's happening for the CS 8 to 7 line right here. It matches predictions if we just run local non-LTE radio transfer just in the location around the gap. And why is this the case? So here I can actually show you a rotational temperature, basically the temperature of the CS gas radial resolve. This region right here, that's right where the planet is that I showed you before. If you have a giant planet there, it's carving out your dust and your gas. So it's taking the gas density quite a bit down, and it's causing this line to be subthermally excited right where that location is. And we see a dip in the temperature that also exactly matches our predictions. And what's really nice about this is because we see this happening locally in a planet-carved gap, we can make an independent inference on the gas density that's right at this location. And if we do all of this, we end up finding that, yes, this can accurately be reproduced by a Jupiter-mass planet sitting in this gap, carving things out. So it's a nice way to use line excitation to actually infer planet properties. Another thing we can also do is we had another 3 lines. We had the molecules. We had the C34S and the 2 H2CS tracers. We can also figure out what their density as a function of radius, and here they are. And then if we take the ratio of those, we actually can do an isotopic analysis. We can figure out if we have too much or too little 34 sulfur relative to what you'd expect in the ISM. You'd expect this just to match the local ISM. But when you do this, the local ISM is here. And in both sets of tracers across the entire disk, you're finding that we have a lot more 34 sulfur than we expect. We're well below in every case. So this is the first time we're actually seeing pretty significant evidence for fractionation, that is enhancement in the 34 isotope relative to the 32 isotope. And we can compare this to other disks. Now, the problem here, as you may notice, we only have a few points. This really hasn't been done too much in the past. You might see a trend. The higher mass disks, those around her big stars, maybe they're a little bit lower than the one disk we have around a low mass star, this Titari disk here. But I would say we're really in a small numbers game right now. This is intriguing, but we really need to do this for a few other sources. And because we had so many lines in HD 163296, we have really tight error bars here. Here and here. And we really need multiple lines to actually be able to provide a robust measurement of this. Okay, so that was just a quick tour through the first project that I want to talk about. Now, in the last few minutes, I just want to mention one way where we can use sulfur to potentially detect planets. And so this is a project that was led by Tomohiro Yoshida, PhD student at NAOJ. And if you remember the last symposium, I talked a little bit about this idea, where if you have a giant planet in a disk, it might heat up the gas, it might cause some local chemical alterations right around where the planet is. And you might be able, therefore, to use chemistry as this new tracer to detect embedded protoplanets in your disk. And so I showed you this system, another disk, HD 169142. Again, the main point here is it's a nearby, face-on, very structured disk in the dust. and it has a planet right here. And this one is a confirmed planet. It's several Jupiter masses. You can actually see it in the near infrared. It moves from archival data. You can see the point source there. So that's very comforting. We know actually we have the planet there. And what I was able to find, I showed last year, was that there was some chemical signatures, some sulfur-bearing molecules, SIS and SO, that were localized right where the planet location is, right here. This SIS was really in the form of an outflow from the planet right here. And then you had a little detached blob in SO that was just a hotspot of gas where we thought that the ice was sublimating and you were getting local formation of SO. So then the big question was, is this unique? Are we able to find more systems like this? I have a bunch of follow-up data that has just arrived, so I can't show you that now. I'll show you that next year. But for now, I can answer these questions at least. And it seems like no, it is not a unique system. Tomohiro led this really wonderful study looking at this another nearby disk called TW Hydra. Again, main point, its morphology could be reproduced very well from models by putting 2 super Earths here. Super Earths, maybe 4 or so Earth masses. I'm going to focus just on this one here at around 40 AU. And what he was able to find is that he detects SO lines, 2 SO lines in ALMA archival data, very much not like a disk. They're sitting here and here, well away from the main dust region. Excitingly, he can fit a ballistic outflow model here. So if you had a protoplanet sitting right here, it could be launching this outflow in the SO that you're seeing. And it turns out when he works all of this out, the best fit planet mass is exactly 4 Earth masses. It corresponds exactly to the model predictions, able to estimate a mass loss rate. And just to say that this is a really unique way to study the early phase of planet formation. And we're sensitive to pretty small planet masses. So this isn't Jupiter's. Now we're down really into super Earth territory. So chemistry might be a unique way to push down to even detecting smaller planets. So almost done. Just want to say the future is bright because we need a lot of lines to do this. We need to actually be able to detect multiple SO lines, multiple CS lines, all of these sulfur-bearing species. And I just want to say that there are multiple large programs across the ALMA and SMA that are doing this. And looking further in time horizon, the wideband ALMA upgrade is going to get us all these lines all at once. So we're not going to have to cobble together all these archival programs. We're going to do one observation and get all of these lines all at once. Okay, with that, I'll end. Happy to take any questions. Thanks.
Thank you so much, Charles. Any questions?
I was curious for concepts like the cute satellite or other, helium escape kind of things. Would it be possible to maybe get 2 different messengers, both with the chemistry approach and then also with observing escape at the same time?
Yeah, that would be great if we could do that. I don't know what kind of resolution you have to actually achieve that. I think that'd be the big issue. But yeah, it'd be great to have multiple things pointing at the same place, where it's really great when we see chemistry and a gap in dust and gas and things in the near infrared and maybe this, right? You want multiple pieces of evidence to have confidence and kinematics as well. So.
Do you happen to know what would be causing this sulfur fractionation?
That's a great question. We are working on that right now. And it goes back to the same idea. Is it something happening in the disk environment that's changing the ratio? Or is it just there was a weird molecular cloud and it just inherited that strange ratio from the molecular cloud that differed from the local ISM? So stay tuned.
Very cool. Awesome. Okay, let's thank Charles one more time. And last but not least, we have our last talk of the session, led by Raluca, who's going to tell us about compact exoplanet systems.
Hi, thank you very much. I am Raluca Rufu from Southwest Research Institute. I'm a 3rd-year Sagan Fellow, so this is my last symposium, and I want to thank the leads for all their hard work that they put in for us. Thank you. So in my Sagan project, I worked on the origin of compact exoplanetary systems. These systems seem to be very common in our galaxy. They are multiplanetary systems that have similar size, usually referred to as peas in the pod architecture. They are Earth to sub-Neptune sized glass, usually rocky. They are compact. Most of the system is within the orbit of Mercury, and their orbital periods resemble more the orbital periods of satellites around gas planets rather than our planets around our sun. But I also want to emphasize an additional characteristics that is unique to these systems, and that is seen if we look at the total orbiting planetary mass and divide that by the primary stellar mass. You can see that there is this common mass ratio. So these systems were selected if they had 3 or more planets, and that planetary system was compact within half an AU. So you can see on a wide range of stellar masses, ranging from TRAPPIST, which is a 0.1 solar mass, up to Kepler-33, which is 1.3 solar mass. So on a wide range of stellar masses, you have this common mass ratio. And 90% of systems would have a mass ratio between 3 × 10⁻⁵ to 3 × 10⁻⁴. So important question to ask, how these compact exoplanetary systems form, and why do they have this unique characteristic? So I'll start with a few observations. The infall from the molecular cloud to the stellar disk typically will last a few 100,000 years up to 1 million years. And the standard assumption is that planetary accretion begins only after the infall ends. And this is true for planets that start to accrete in orbits similar to Jupiter. But for these compact systems, the accretion, because of the orbital periods are so short, the accretion can be very short as well, sometimes smaller or comparable to the infall timescale. So maybe accretion has started during the formation of the stellar disk. And there are some signs in ALMA data that show that accretion may have begun in systems that are relatively very young, less than 1 million years old. So if planets indeed started to accrete during stellar infall, would they be able to survive? And if they survive, what are their characteristics? So I'm going to start with this model, and we're going to assume that planetary accretion indeed started during stellar infall. So you have the molecular cloud that has gas and dust that falls onto the star, but because it has too much angular momentum to be accreted directly onto the star, it forms a circumstellar disk. And this circumstellar disk is initially has orbits up to centrifugal radius, let's say r sub c. And this r sub c is just a measure of how much angular momentum is in that initial molecular cloud. So for compact systems, we assume that the angular momentum is relatively small, and most of the material is going to arrive close to the star. And maybe in our planetaries, in our solar system, that r sub c was much larger, and that's why we formed Jupiter. So the gas disk is in this quasi-steady state between the infall and viscous spreading. Initially, the dust is coupled to the gas particles, but once it's in orbit, it starts to collide with other dust particles and starts to grow in larger and larger aggregates. So the larger sized dust particles will decouple from the gas and will preferably remain inside the inner region, while the gas itself is going to viscously spread outward. So with time, the disk metallicity will increase and will produce favorable conditions for planets to form. So planets accrete in the inner disk, and as the planets grow, they start to fill type 1 migration. And eventually the planets will reach a certain size, which we call M-crit mass, at which their further growth timescale is comparable with their migration timescale loss. So planets that reach that size are going to fall inward onto the star, but because the dust is still being supplied by the infall, new planets can form to replace those planets. So you have generations of planets that form, accrete, migrate inward. And eventually the infall will end, the gas disk will dissipate due to viscosity and photoevaporation, and the type 1 migration will slow down. And under range of conditions, which I'm going to talk about, some planets will be able to survive the disk phase. So in order to test this, we did n-body accretion simulation during infall. We mimic the infalling material by adding planetesimals in the inner region with a timescale that is exponentially decaying in a timescale of tau in. we include inward type 1 migration, that its acceleration is proportional to the surface density of the disk. And the surface density of the disk is in this quasi-steady state between infall and inversely proportional to the viscosity of the disk. And for viscosity, we just assume a simple alpha disk model. So the surface density is going to decrease exponentially on a time scale tau g. So you have two time scales that are going to be important. The tau g is just the dissipation of the disk, and tau n, which is the rate of the infalling material. And we are going to simulate the last few to 10% of the stellar mass. So until now, I kind of told you that the migration is continuous and there's no cavity inside the inner disk. But sometimes in hydrodynamic simulations, there is, in the inner regions, there might be depletions of the surface density due to magnetic truncation. And in such configurations, this inner gap can act as a planetary migration trap. So in order to test this, we also have simulations that use when a planet reaches that inner edge, it's going to stop the type 1 migration to occur. So I'm going to show you some of the results. The first one on the left doesn't have any cavity. The dashed line there is the M crit, the critical mass, for which the time scale of accretion is comparable to the time scale of migration. So you can see that planets would start to accrete. They will reach that dashed line and eventually going to migrate inward and are going to be lost. But other planets accrete and form and replace those. So there's a few generations of these planets. Eventually the surface density decreases and migration stops. So the second one does include a cavity at around 0.1 AU. And you will see that it's a bit similar to the previous one in the sense that it is going to, planets are going to migrate, accrete, migrate. And then if you look very closely, you can see that the planet stops for a second, but then because the outer planets are still migrating inward, they're going to push the inner planet inward. So you still get the accretion, migration, and loss mechanism as you saw before. So just looking at the no cavity cases, just because it's a bit more continuous and simple, on the y-axis here, you have the total planetary system mass material normalized by the stellar mass as a function of the time. And each color here represents different values of tau g over tau n. So how long the gas dissipates compared to the infalling material. And you can see that for fixed disk properties, so for fixed viscosities and for the similar infalling rate, all of the systems reached a common maximum system mass ratio. And for increasing tau g over tau n, you can see that you're going to lose more planets, and therefore the final planetary system mass is going to decrease over time. And this is because migration is more significant than accretion if the disk is prolonged. And you can further see this in this figure. In the y-axis, you have the final total planetary system mass ratio over the tau g over tau n. The black dots are the n-body simulations, assuming no cavity. The red ones do assume a cavity. And the dashed line here is just the analytical model, which I didn't have time to talk about, but you can marvel and see that everything kind of matches the numerical simulations, which is always great. So the final planetary system mass is a bit larger when the cavity is included, just because it needs more material in order to push that inner planet. And an important question to ask is, what is the typical tau g over tau n for compact systems? So in order to answer this question, we performed 1D gastic simulations that include infall, viscosity, and photoevaporation. And we find that for compact systems, this tau g over tau n is relatively small, up to 2. So this means that maybe for our solar system, tau g over tau n may have been larger, and therefore we don't retain a lot of the masses. So you don't retain most of the masses that are accreted during infall. But for compact systems where the material arrives very close to the star, where photo evaporation and viscosity are more efficient, then tau g over tau n might be relatively small. So we expect for compact systems to retain about 20 to 40% of the maximum accreted mass during infall. And we can also look at the disk properties and see here in the y-axis, you have the final planetary system mass ratio, and the x-axis, you have the viscosity of the disk over the gas to solids in the infalling material. And you can see that although we ranged the alpha over f are 3 orders of magnitude, you only get 1 order of magnitude variation in the total planetary system mass. So there's a relative weak dependence on these properties. So for likely compact disk properties, we are able to reproduce the few 10 to the minus 5 to the 10 to minus 4. And this is important because this is the first model that is able to replicate the near equal occurrence of close super-Earths around stars of wide range of metallicities. And this is because the cycle of accretion and migration and loss, therefore the stellar metallicity is going to not have a very hard dependence. So to conclude, if accretion starts early during infall, then planets are able to survive this period, and they're even with standard type 1 migration and even with a cavity. And we also show that with a cavity, things are very similar. The alpha over f and tau g over tau n will control the mass of the surviving planets. And for compact systems, we saw that this tau g over tau n is relatively small. And for a large range of viscosities and disk properties, we are able to replicate the observed compact systems of a few 10 to the minus 5 to 10 to the minus 4. Thank you.
Any questions?
I don't know if you said this, but do you integrate your solutions? Like, how many of those planets survive if you integrate the equations for like 5 years? Because I think you are evolving the system for very shortly, but how many do you survive?
I evolved the system for about, depending on which of the viscosity I take, but maximum of 30 million years. So after the gas disk dissipates, there's no more migration. There could be additional evolution of stochastic, like planets are not stable and maybe impact each other. So there could be some further evolution after the gas dissipates.
This is like a upper limit, like a number
Yeah.
of the total mass of the state, I guess.
Yeah. But the total planetary system mass is not going to change. Maybe the architecture of the system would change a lot after.
Awesome. Let's thank Raluca and all the speakers in this session one more time. And I think we have a 20-minute break, so back 5 minutes for
Hello. Hello. Anyone hears me? No?
Hello. Can you hear me?
Hello.
Hello? Hello?
So for the remote presenters, should we share screen or they will share screen? How does it work? Anyone knows?
Hi. Hello.
I'm advising students.
Hey, could we check again?
Yeah.
I mean, I didn't change the slide
Okay.
since the last like I loaded them.
There's no new version or anything. Yeah, but we can pull it off.
And can I do like presentation
Yeah.
from here? Like this?
Yeah, that's fine.
Okay, and then it'll show me the time. It's good. So I didn't.
Yeah, and we'll have a, and there will be a flag going.
Yeah.
Yeah, that should be fine. This advances, right? Yeah, cool. Okay.
Advances?
Yeah.
Like that.
Big button forward and the small button is backward.
Ah, I see. Backward. That's great. Thank you.
Yeah, of course.
Perfect.
Yeah, not a problem.
My mouse up to the.
Yeah.
So Bluetooth mouse.
Does have a disk, is not a disk. And then is that fraction reflected? An estimation.
So you can click through.
This is probably going to be a lot more pleasant than the limitation.
Yeah, yeah.
So back to the whole like scholar activities. I wonder if we could go again, just like the Cambridge slip observations, stars. Probably still doesn't do that. Totally fine. But
I like to see.
so there's no much different. Surprises me.
Yeah.
So flares are fundamentally trace all the way, all the way through. And so the millimeter is part of sort of chasing that mission, magnetic reconnection and accelerating the charge particle. Mission, so that's what we see first. So that's like long observations and our surveys of the market space, whatever you can get your market. And then you go to the star things, and then you're the first slide. And then you start to get the more gradual forms of it. So you'll start to see a prompt optical flare. You'll get a prompt memory R flare, which is a little slower still. You'll get soft X-ray flare, which is a fairly loose, so like people are the longest. And then after the gas fluxes are this long so yeah, and the radio you also get emission. Yeah, they're very in part seconds. And the flares are around 30 seconds to 10 minutes. And the optical is there's stochastic movements, but within flares, sometimes you can get structures. We think that the ribbons are actually also there's different movements and to sausage and that. Because we're very like that growth star, and the invert makes it very easy to so that it gets harder and harder as you get your star. It's not certainly not impossible, but just it's more challenging. So you're going to see until wide single variation results. So you get really I'll have to go out So that might give you a very, very first order, right? But some of this for a decade, extra observations are still the best one to go. More than availability and the spin down takes so long. Yes. It does get extra luminosity.
Oh, so, yeah.
Okay, when you heading back? No. Oh, sorry, yeah. Oh, Steve, yeah, it could be. Yeah. Oh, sorry, behind that.
All set.
All set, okay. Okay, so that's, you have to, it is. Okay. Make it look flat. This is the start. Great.
Other announcements after about Dennis lunch.
I think that there will be,
All is around.
I've got to find Frank. He's gonna be around. So I know that house.
All right, hello everyone. Let's get started. Settle down. Welcome to the last session on the penultimate day. This will be a session about ISM and stars. We have 6 talks before we all go to dinner, so we'll try to keep on time. Our first talk will be online by Sultan. Sultan, can you hear us?
Yes.
Okay, do you want to start? And I think you'll get a message in the chat when you have about 2 minutes left.
Sounds good. Thank you very much. I'm very sorry to miss being there in person. I'm probably missed a nice dinner and lots of nice evening drinks. So I wish to, I look forward to being there in person next year. So I want to share with you some of the science that I have been doing within the Learning the Universe collaboration. And this is mainly to address the question, the surprising results from JWST and the big debate we had in the field. So let's get it started. So basically, JWST have revealed the high redshift universe and over expectation, right? So we have the detection of these bright sources. This is the luminosity functions at redshift of 10 and 13. And we see that like most of the models, regardless of the recipe you use in your model, fails to reproduce these results, right? And most likely what is needed here for the high redshift regime, right, is to have too efficient star formation. Then the question is that how do you get that, right? So we have a really tension between the theory and the observation. So you could actually just, to solve this tension, the easiest way to say, oh, maybe the observation is wrong, and then we go home and that's it. And that's probably also true because there are some systematics, right, in the way to measure things, right? So in photometric and spectroscopic redshifts, there is a big debate here, right? And okay, so let's exclude that option. Let's assume that the observers have done a nice job of doing all this and everything is correct. Now, how do we solve this from our end? Because this is where the interesting science comes in. So it could be mainly inaccurate predictions from our case, in our side. So maybe the way that we model cosmology is wrong, and maybe you can say lambda CDM is wrong, and you can invoke your favorite scenario to boost halo mass function so you can get efficient star formation. Or maybe the way that we do this mock observation, right? Like the pipeline for adding dust and all that. Maybe we don't know, and nobody probably knows how to do this in high redshift. So maybe there is an issue, but the dust maybe goes into the opposite way. It will suppress the luminosity function further. So maybe the problem in the astrophysics that we don't know much about, right? And that's probably mainly true. Most of the models we have, we are constantly refining them. And in the astrophysics, there are many things, right? We heard about weak feedback in high redshift to do the efficient star formation. We heard about different directions here. But what I would advocate for, maybe it's more about the way we model star formation. Maybe it's mainly because it's too efficient star formation. Maybe we don't model star formation correctly. So let me take you to how we model star formation traditionally in simulation. So the basic idea you have, this is one of the most successful models, the Sprengel and Henquist model, 2003, right? Multi-phase model, you form stars based on the amount of gas. So the star formation basically correlated with the cold gas, and you have a parameter for the time scale for star formation. And what you see in this plot, this is the famous Schmidt relation, right? So the correlation between the star formation, surface density of gas, and what you see in the dashed line here, this is the observation. And one of the earliest attempts is to implement this model. And what they realized here is that if you tune the time scale for star formation to 1 gigayear, you match the observation. This model has been really surprisingly successful, even at high redshift when you tune to the local observation. It's really very successful in many scaling, reproducing scaling relation. However, we don't learn much, right? If you tune to the observation, we should have rather a predictive model that physically motivated model that once you plug in everything from the first principles and from small scale physics, you naturally recover the observation, and then maybe that will tell you maybe you need to add something and you need to tweak something. But when you collaborate to the observation, you don't learn much, right? And that's the exercise we're doing here. And there are other motivations here, right? This model does most of the models in the market. They don't really capture these ISM conditions, varying ISM conditions. Maybe also they depend on the mesh and the resolution. So if you go to different resolution, you have to tune your parameters, as what happened in TNG 50. If you go to the multi-phase ISM is not resolved properly. So many things that are missing. So this is an attempt to account for that. So we have a great progress in the ISM simulations. This is one of the simulation Tigris simulations developed by Eve and Chango in Princeton. And this is really just like 1 kiloparsec scale, high resolution. You can think about it in one of these simulations as just a slab in a disk of a galaxy, right? And you model the evolution of the gas in this extremely high resolution, and we can't really resolve this in large scale unless quantum computing kicks in or something, but it's very hard to have this small scale resolved. So the question is that can we use recipes from here to inform modeling star formation on large scale, and that's the game we are after. So that led to the development of the pressure regulated and feedback modulated model. And it has two assumptions. The first one is the ISM conditions and the star formation is co-regulated each other to achieve equilibrium in any system. And from that, you can drive some relations and basically based on the equilibrium in the vertical equilibrium. So the pressure is similar to the weight if you are in a vertical equilibrium within any hydrodynamical system. And the pressure could be written as a function of the sigma squared, which is the velocity, and rho g, which is the volumetric density of the gas. And then the pressure will have different contribution from thermal, turbulent, and magnetic field. And you can do also the same for the gas, where the weight basically you have contribution from gas and star and dark matter. And when you account for all these equations, this is the basic, it's just analytical equations, you can come up with some recipe for how to model the gas height, HG, which is gas height is very uncertain. And the last one is how do you get the star formation? Once you have this relation set between the pressure and the weight, you can have some feedback modulation and yields, and these basically the star formation is more correlated to the pressure than what you see in the Schmidt relation. Okay, so this is nice old theory. What are the parameters we're missing here? There is two parameters we're missing. Sigma effective, which is the velocity of the gas. We don't know how to model on large scale. And also the epsilon, which is the feedback. How do you model that? And these, we get them from ISM simulation. So the first one is the gas velocity. So you can look at the Tiger simulations, which is these are the 6 simulations that I have showed you a couple of slides ago. And you see here these, they have a correlation between, of course, the pressure and the density. And then you can actually have a relation and you make a fit. You use that fit of the effective equation of state with the equation of the sigma squared rho g, and then you can come up with the relation how the sigma effective related to the gas to the pressure. So now once we know how to calculate the pressure in the simulation, we can predict what the velocity of the gas. And for the yield, you can compute this directly from the ISM simulation, and you look at it, and then you see, of course, the feedback is very wild as a function of pressure again. So you need to look for the median relation, and then maybe you can approximate a fit for that. And then you can say, well, this is really a good representation. We can plug in a large scale. So we know now how to model gas given the pressure, sigma gas, velocity of the gas given the pressure, and also the rho total, the epsilon, the feedback given the pressure. Okay, so we know now. So our theory is kind of complete. So now how do we do this? So this analysis is just in post-processing to proceed. So we go to TNG 50 simulations. We select galaxies from stellar masses 10 to the 7 to 11. We assume that we have a result system. So the minimum is 100 particles in all time. And then we have a star formation threshold. So we don't go to a very unresolved systems. And you go to the simulation, you pick up any galaxy, you have the angular momentum direction, you rotate face on, and then you grid your galaxies, and then you can compute all these properties like what is the star formation surface density, what is all the properties that you have seen in a couple of slides ago, you can all compute them, okay? And then you can just try to make predictions with the star formation model given these local ISM properties that I have, we have here to compute the weight, to compute the pressure and all that. So let's get to the results. So the first exciting results we get here is that the relation between the depletion time and the dynamical time, which is another proxy for the star formation. And what you see, this is a busy plot. So what you see in the depletion time in the y-axis, dynamical time in the x-axis. On the left, this is the prediction from our model, the BRFM, and on the right, this is the traditional methods. And of course, the traditional methods really match these lines and these like diagonal lines. These are some reference lines. And the TNG 50 has, like, this model has been tuned to this, so it's not surprisingly that it reproduced this. But in our case, we have this nice prediction that as you go to smaller depletion time, you get even a smaller depletion time, which means that you don't predict constant relation between the dynamical time and the depletion time, which has very nice implications. Then we look at the level of the global Schmidt relation, and this is the same, right? So this is in the left-hand side. This is the surface density of star formation. X-axis, the surface density of gas, and left is prediction from our model BRFM, and the Springle and Hequist is from in the right-hand side. What you see in the blue stars, these are coming from the ISM simulations, and the diagonal lines coming from different observation, whether you account for molecular gas or not. And everything, the color codes here coming from fraction of star formation, anything in dark color, center of galaxies, anything in light colors, the outskirts. And what you see here, of course, in what you see in the right here, the Springle and Hequist is really tuned to this observation, so it reproduces it very nicely. But here is our prediction. Let's go through them. So the first prediction here is that you have, whenever we are in the regime from 1 to 100 megabars solar masses per parsec squared, we match the observation without tuning. And that's exciting, right? So now we don't tune to the observation, we tune to the ISM. We are able to match that whenever we have data from the ISM simulation. And the other prediction here is that we predict two efficient star formation at high densities, okay? And as you see here, and that's purely extrapolation, but that's really, and we are running more simulation to verify this, but this is how you think I'm going to explain the abundance in high redshift, because as you go to high redshift, the density is higher, and you naturally get the two efficient star formation. And you can see it here. So this is the luminosity functions at redshift of 9, 11, 12. And then what you see in the solid line, this is the Springle and Henquist model prediction. In the dashed line, these are the PRFM models. Whether you model the sigma and the epsilon as a function of pressure only, or you account for metallicity evolution, that it doesn't matter. But we see this boost because the model predicts shorter depletion time at high densities, and that leads to two efficient star formation at high densities. And we naturally, as compared to this observation, we naturally getting closer to the right answer. So this is how we solve the puzzle, and we think this is what's happening probably at high redshift. So in conclusion, this is my takeaway. I think we predict shorter evolution time, and that leads to efficient star formation at high redshift and high densities. And we are consistent with the observation without even tuning whenever we have this ISM dataset. And this model might naturally explain this high abundance at high redshift. And we are currently within the collaboration going on through implementing this model in the fly. And thank you very much for listening.
Okay, are there any questions? Maybe one.
Thanks, really nice talk. Just wondering if you have any idea about what the physical interpretation of the shorter depletion times might be, or the physics.
I cannot hear properly the question.
So the question was if you have any physical understanding of what might be driving the shorter depletion times?
So that's mainly because we think that's mainly because this is coming from here, because the yield is really has this nonlinear relation with the pressure. And as you go to these high redshift, this is what pushing everything to shorter depletion time mainly.
Okay, thanks so much. I think we're going to move on. Let's thank Sultan again. Okay, so our next talk will be what I think is the only astroseismology talk of the conference. And Bill will tell us about core envelope rotational misalignment in Kepler 56.
Hi, everyone. I'm Joel. I'm a Hubble Fellow at the University of Hawaii. And yeah, this talk is an imposter. This talk has nothing to do with star planet formation, but I hope maybe the exoplanet people will find it interesting. So, all right. So, as I am introduced, I am basically the only seismologist here. So I think I have to explain a little bit about how seismology is relevant to the science project I'm about to talk about. So seismology is really the study of normal modes in stars, right? You have standing waves, and these standing waves are observed either through time series velocities or time series photometry. When you have a time series like this, you don't actually look at the intensity variations in the time domain. Rather, you look in the frequency domain and you see peaks in the power spectrum, each of which corresponds to either a normal mode of oscillation or occasionally photometric rotational variability, or if you have God's own photometer, you can get baseline for rotation as well. But as far as today is concerned, we'll be focusing mostly on the seismology, which lives here in the power spectrum. So if you look more closely at this part of the power spectrum, right, if you're lucky and your star is a convection zone, you see a series of repeating peaks like this. Right, this is the characteristic signature of a solar-like oscillator, where every mode that can have kinetic energy will have kinetic energy. And this assumption greatly simplifies how we interpret the phenomenology of these peaks. So one thing we can do from having this many mode frequencies at our disposal is kind of do something similar to the CT scanning you see in an airport, right? And you kind of infer the internal structure of the star. But for today, we will mostly be interested instead on using this to constrain the internal rotation of the star. Okay, so the way this works is that you have normal modes. And if you remember your undergraduate quantum mechanics or something, the normal modes have shapes in the horizontal direction, which in a spherical star are given by the spherical harmonics, right? So the spherical harmonics of degree L have 2L plus 1 degeneracy. So the bigger the L, the more degenerate modes oscillating at the same frequency. Some modes appear to be propagating around, in the prograde sense, around a notional axis, and some appear to propagate in a retrograde sense, right? And that notional axis could be the rotational axis. So if you were to have these modes propagating like this in a rotating star, then in the stationary frame, your reference frame, you would see the modes that propagate in a prograde sense will seem to you to propagate, to oscillate more quickly. And those which propagate in a retrograde sense will appear to oscillate more slowly, right? So the frequencies will change in the non-rotating frame. The axis of inclination of the rotational axis relative to you, the observer, will also determine which modes appear to cancel out geometrically when you integrate over the visible disk, and which will appear to oscillate the most prominently. So for example, for a pole-on star, you only see the m equals 0 mode, and for an equator-on star, you see only the modes of the same parity as the degree. So observationally, what this means is that if you see a peak in the power spectrum in a non-rotating star, rotation will turn that peak into multiplet, right? With the number of components in the multiplet being determined by the degree L of the mode, right? And with the inclination axis of the star determining the distribution of power between components of the multiplet. So this is how we ordinarily would infer the geometry and rates of rotation from seismology with one rotational axis. Okay, so now I'm going to go maybe a bit off the rails and consider a situation where a star has two rotational axes. And you might be wondering what the heck's going on, right? Why would we even need to consider such a situation? Well, the first is that stars don't tend to come alone. They often have planets. And these planets are often misaligned, and they may occasionally interact with these stars, either tidally or perhaps by getting eaten, right? So if you have a star in a misaligned orbit, for example, that gets eaten by, a planet in a misaligned orbit around a star that gets eaten by the star, it will deposit this angular momentum in the outside bits of the star, and consequently, the outside will potentially rotate around a different axis than the inside, right? So this is the physical scenario that we want to be able to at least diagnose in our observational data. So I'm not going to go through the extension to mathematical theory that has to, the mathematical theory of oscillations that has to take place before we're able to interpret these oscillations. But I can give you a rough overview of the physics of a particular class of stars that reveals this kind of differential rotation most naturally. So these are red giants, which support the propagation of two different kinds of waves. So stars like our sun, which are convective on the outside, they support the propagation of pressure waves, sound waves, the kind that I'm making as I speak, right? Red giants, or more generally radiated parts of stars, also support the propagation of buoyancy waves or gravity waves, the kind that you see propagating on the surface of a body of water if you were to throw a rock or punch the water surface. So these two kinds of waves have different dispersion relations, but in the red giants, they couple to each other in a way that permits us to distinguish between P modes, which are sensitive to the surface, and G modes, which are primarily sensitive to the core. So here I showed the integrated sensitivity functions. You can think of these as cumulative distribution functions, right? And the red dotted line shows where the G modes are sensitive to. So where the slope is high is where the G mode is sensitive to, and in the exterior part of the star, the integrated sensitivity function is flat. So the actual sensitivity function is 0 outside of the core. Likewise, the P modes shown in gray are only sensitive to more or less the outside of the star. Okay. So the way this works is that we don't actually have observational access to P or G modes and red giants. We see peaks in the power spectrum, right? And over the course of stellar evolution, what's going to happen is that the frequencies of G modes increase over time, and the frequencies of P modes decrease over time, right? And ordinarily, you would be able to identify a pure P mode or a pure G mode just by its relative amplitude. Unfortunately, life is not so simple because the two mode cavities kind of talk to each other. And so if you were able to trace the evolution of a power spectrum over time, you would see that G mode and a P mode, whenever they come into resonance, kind of interchange characters. Like this. This is called an avoided crossing. It makes life very painful. And the trick in seismology, in red giant seismology in the last half a decade or so, has been to figure out how to recover the pure P and G mode frequencies from this kind of nonlinear interaction. Okay, so rotation complicates matters because the core also rotates more quickly in most red giants than the surface, and when you have multiplets interacting in this nonlinear fashion, it makes the phenomenology extremely difficult to interpret. But we try. Okay, and yeah, there's also this inclination thing, which I'll get back to later. All right, so to describe the geometry of the situation, earlier I have shown in all my figures a single inclination angle of the rotation axis. And in order to parameterize what we're about to see, I need to describe the geometry. Oh, wow, it's not showing up very well. This is supposed to be a sphere. I'm not sure if you can see the gray, but this is a triangle on the surface of the sphere. The line of sight is, shown as LOS here. And we now have two inclination angles, one for the core, with the core's angular momentum vector pointing this way, and one for the envelope, with the envelope's angular momentum vector pointing this way. The misalignment angle, beta, between the core and envelope is shown here with this geodesic. And there's a third geometrically degenerate angle, which we cannot usually constrain from seismology, that's shown here. Okay, so this is the overall geometry of the system. So the idea here is that in a red giant, we have G modes, which are primarily sensitive to the core, right? And P modes, which are primarily sensitive to the envelope. And ordinarily, we assume that the two inclination angles are the same, right? So when we lift this restriction, we might, for example, have a core that is seen, not very, hold on. And then we might have an envelope that is seen closer to equator one, for example, right? And then this additional obliquity angle just more subtly changes the mode frequencies a little bit, right? So by lifting the constraint that the core and the envelope have the same inclination angle, we can generate more interesting power spectra than ordinarily possible. Okay, so with all this set up, we are now mentally equipped to have a look at some data that Kepler took for us a long time ago. I will describe in particular Kepler 56, which is, for those of you who are not exoplanet people, this is one of maybe 3-ish exoplanetary systems where we have multiple planets which are transiting and are unusually aligned, but which are all misaligned from the rotational axis of the star, right? So you have spin-orbit misalignment with multiple mutually aligned planets. So the discovery paper for Kepler 56 is more than 10 years old now, right? And the geometry of the situation is that it has two transiting planets, a misaligned spin vector for the star, and then an outer planet, which was not constrained well at the time. So this is what the distribution of inclination angles for the P and the G modes look like in the original discovery paper. And they suggestively appear not to be quite the same, right? But the mathematical devices required to describe mixed modes had not been developed at the time. This is what the power spectrum looks like for Kepler 56. And it is very suggestive of, being a spin, internally spin misaligned system, right? And so with the benefit of this new mathematical theory, we can do a more robust fit of a parametric model, including core envelope misalignment against the power spectrum. And we can revise the two posterior distributions for the core and the envelope, and they are different. So the reanalyzed posterior for the core's inclination angle is very similar to the original discovery paper, but the envelope appears to be more or less consistent with being aligned with its transiting planets. Okay, so the implications of this are kind of interesting, right? Because it means that we've kind of killed off one of the three known spin orbit misaligned planets with mutually aligned planets. And that has kind of interesting implications for how these misaligned orbital architectures form. The other thing that we might want to revisit with this in mind is the fact that essentially every other constraint of spin orbit misalignment that we have relies on measurements of surface rotation, right? And seismology gives us internal rotation. So it may very well be that the population of internally spin misaligned planets is larger than internally spin misaligned stars is larger than we might suspect. So I've run out of time, so I will leave it here. Thanks for your attention.
Okay, do we have time for a question? Anyone?
What software did you use to make that very first one?
We can talk more about that later, but the 3D stuff was written in 3.js. It's like an OpenGL library for web browsing.
That is very cool.
Any science questions? Okay, Black Tim, I'll show that.
Super cool talk. You alluded that there might be larger samples. Do you have plans to apply the model to a larger data set? You obviously picked out the one that you expected to see. Do you have thought on how you can
So I've only done a very small preliminary exercise, and this is the only one I found in that rather small sample of like 5 or so stars. Stars are assumed not to spontaneously misalign themselves, right? So we would expect this kind of physical situation to be rare. But I think placing constraints on how often we find internal misalignment would be valuable, and that's the next thing I'm going to. I think more is good.
I think we should move on. Thanks so much. Thanks again. Okay, next up we have Peter, who's going to talk about unraveling the most distant massive star populations with our next door neighbor.
Yes, thanks so much. And yeah, I put this in my in the talk title I submitted, so I have to try to go from Redshift 12 back to 0 in 12 minutes. So we'll see how well I can do that. But yeah, so massive stars we think played a very important role in the very early universe. You know, they were forging the very first metals. Probably they were the dominant source of the ionizing photons that reionized the universe, although lots of debate about this still. And they also probably played a role in seeding and certainly feeding the first massive black holes. And the exciting thing is that JWST is finally giving us a direct view of these objects spectroscopically. Of course, we already had a clue from Hubble. Hubble was very good at taking deep images and finding the first of these galaxies at redshift beyond 6. Not so good at taking spectra. These are actually from the ground. But interestingly, even these bad spectra from the ground found emission lines in a number of these objects. In particular, this extremely prominent carbon-4 emission. So this is triply ionized carbon at 20 to 40 angstroms, unlike anything we had seen in lower redshift galaxy samples up to this point. So it's not going to do it. Okay, well, anyway, this is going to cover up some of the this point. Let's see. Right, and you might laugh at this detection, but this is real because we now have a JWST follow-up spectrum of this object. And in this stack of medium resolution data, this carbon-4 is clearly there, and it is indeed at above 30 angstroms. And alongside it is this nitrogen-4 line. And this is basically never seen, despite our best efforts to find examples nearby that show these sorts of emission lines. We can find carbon-4 emitters at redshift 0 that are finally actually getting up to this range. This is showing some in-prep work led by this great CASI student, Lauren Henson, who's going to be starting at UCR as a grad student just next week, I think. But her work shows that we're getting up to these carbon-4 equivalent widths, but even in these objects, you're not seeing this nitrogen-4 anywhere near these strengths. And this pattern is popping up now in a number of these systems at the highest redshifts, including some of these universe-breaking objects, the most luminous objects we know beyond redshift 10, including this galaxy up on the top right that Rohan found in some of the first imaging from JWST. The spectrum of this and GNZ11 both show this extremely prominent carbon-4 and nitrogen-4. And so this is pointing to this pattern of highly ionized and nitrogen-enriched gas in a growing sample of these objects. And this is really peculiar because this is an abundance pattern that we basically do see in the oldest galactic structures. So we see this in every globular cluster for a long time. We've known about this peculiar abundance pattern in these second population stars. It also might be present in the oldest component of the ancient Milky Way halo. But we basically see that nowhere else. So if you look at H2 regions and galaxies at lower redshift, basically represented by the blue points here, these live in a totally different portion of this OH and O parameter space. And we've known about this for a bit in the globular clusters, but we really don't know what's producing this. It's a hotly debated origin still, except I think, what I'll put forward is that we do kind of know where we get this nitrogen. Because massive stars produce nitrogen quite readily. So if you're burning hydrogen at high temperatures, like you see in any massive star above 8 solar masses, they're going to be burning hydrogen via the CNO process. And this takes carbon, nitrogen, and oxygen as catalysts, and basically converts all that CNO into nitrogen almost entirely. And so all massive star interiors have substantially nitrogen-enriched material in there. The problem is just getting it out. So what is going on in these redshifts beyond 6 galaxies and in these globular clusters is kind of a linked question now to some degree. I'm going through a lot of this just to highlight, we're seeing low metallicity, but huge quantities of nitrogen and a hard ionizing radiation field, but not quite hard enough to necessarily imply some non-thermal spectrum from an AGN. And what I would like to motivate based on where we think nitrogen is being produced is that this is telling us that these early massive star populations are doing something quite interesting. And one possible thing that these massive star populations could be doing that we don't necessarily have the best models for is interacting. So we know most massive stars have close companions, in fact, that are close enough to interact during their main sequence lifetime. And this interaction very readily will strip the donor star of its opaque envelope of hydrogen. So you're removing all of this nice fully envelope of hydrogen and exposing this very hot core, and also all its nitrogen-enriched material. And it also does a lot of other things. So I'm just going through a sequence of things, highlighting the impacts on ionizing radiation and on yields at these for these early times. But beyond stripping, this also very readily spins up the mass gainer. All that material is being transferred, if it's conservative at all, will end up transferring some of the angular momentum of the orbit to the other star, spinning it up. That also generically yields a hotter star. And we know this is a messy process. You can see examples of this in the Milky Way. You can take images actually of ongoing mass transfer, and it's messy. There's a ton of circumstellar material being thrown off. And so this also very generically ends up polluting the ISM with a lot of material that has seen nuclear processing inside of a massive star. And actually there are papers, including this nice one by Selma de Mink, highlighting that you can kind of get close to globular cluster sort of abundances with some pretty conservative assumptions about how this proceeds. And it also, this is important because this should work even at very low metallicity, where normally certainly for where we expect the winds of these massive stars should be quite weak. These are driven by metal line absorption. And so the classical ways of getting this material out of stars, like in Wolf-Rayet stars, should not be operating because these winds are too weak to actually strip this envelope. But binary evolution should still work. We should still have binaries. They should still interact. And also, this process should be strongly enhanced in dense clusters where you have a lot of dynamical interactions that can harden binaries and force these things to interact. So, maybe this is at play here. But people have been focusing on trying to incorporate this into models for population synthesis that we can use to reproduce nebular line emission for quite a while. And this work is very complicated and involves a lot of assumptions. and is ongoing, but we think help quite a bit for explaining this high ionization emission, in particular for explaining these very strong helium-2 and carbon-4 lines. These models do get you into this zone, depending on which modeling framework you ask. But that's highlighting the fact that this is highly dependent on assumptions, and different models will tell you that you can solve this helium-2 problem at certain metallicities, while others will say that you cannot. And so this motivates to actually calibrate these models and understand what's going on in these early systems. We need to actually find examples of these objects. And so we can ask, can you actually find stripped or spun up stars that we think were impacted by mass transfer and actually test these predictions? It turns out it's very hard to find these. They're very readily outshined by their companions in everything but ionizing wavelengths, we think. But you can go to the ultraviolet and get close. And so we've now started uncovering, so this is amazing work led by Maria Droud and Ilva Gottberg in the Magellanic Clouds. We started uncovering these populations of stars that I think are pretty uncontroversially the products of mass transfer and of envelope stripping, and that live somewhere below the Wolf-Rayet sequence, but at very hot temperatures that you can't get to otherwise. So these are starting to be built up, but this is only in the clouds. And the small Magellanic Clouds, the 20% solar, this is a lot more metal rich just in oxygen, and certainly in iron than we're seeing in these early galaxies. The iron abundance in these first systems is dramatically different from what's happening in the clouds. So we really want to be able to calibrate this stuff at lower metallicity, because right now you can test these predictions in the Magellanic Clouds, but it's essentially entirely theoretical, extrapolating the below 20%. And in fact, we're just now really starting to dig into this. So there's a number of groups working on this, trying to pick apart the nearest dwarf irregular galaxies beyond the Magellanic Clouds that get you to a little bit lower metallicity. And this is really hard. We just don't have a very nice star-forming galaxy that is in a current burst that's within a megaparsec. But there are a handful, and you can see here work led by Maud Gull, assembling spectroscopic samples across a number of galaxies. So this is Leo A, Sextans A, the single O star in Leo P, showing that we're starting to populate the top of the main sequence here. And some of the more evolved stars off this main sequence, it's getting up, it's not probing the highest mass stars that we think might dominate the ionizing output of a burst, but there are already some surprises here. In these populations, and you can kind of see this, by the way, that some of these, I guess actually not in this diagram, but in the color magnitude diagram, you can see some of these stars actually are a little bit redder than they should be. You're seeing some weird things in the winds and also in evidence for circumstellar material that may be indications that there's a high incidence of mass transfer and certainly of binary companions in these systems. But this is somewhat subtle. There's also, and I want to highlight this object I've been thinking about a lot recently, and it should be out very soon. There are some less subtle indications of weird things going on at these lowest metallicities. And so this is an object in Leo A, one of these below 20% solar galaxies. It pops out very clearly in the FUV, and we targeted it thinking that it would be like a normal OB star. But in the optical, this thing is almost blank in the continuum. Fairly blue slope, but booming emission lines, and second in prominence next to H alpha is helium-2. And that's quite weird and should get you quite interested immediately. And we got an HSC follow-up spectrum of this thing, and it confirms that this helium-2 is actually probably not in nebular gas, but rather in a wind. You can actually see the helium-2 1640 profile in P Cygni along with carbon-4. But this also suggests, confirms the picture. This thing is extremely metal poor. You can barely see the iron at the left-hand side here. Quite nitrogen enriched. There's prominent nitrogen lines here. We've carved down into material that has seen CNO burning, but also driving a wind, which should not be happening, and certainly shouldn't be happening at this extremely low velocity. And the picture we put together here is that a lot of this makes sense in the context of being a partially stripped star at very low metallicity. It's hotter than anything else in Leo A and hotter than the population synthesis models would predict without any sort of interaction. It's not quite as hot as the helium burning main sequence, which suggests maybe indeed that there is some residual envelope. But this wind is basically an order of magnitude higher than any of the predictions from evolutionary models would expect. And basically, takeaway is that there's nothing like this in any of these pop synth models. And it confirms that binary interaction is probably playing an important role here, but maybe not in exactly the nice, clean ways that we expected. And so a natural question, I'm running out of time here, but natural question is, can we find more of these? And just want to quickly highlight Ilva, who's now moved on to ISTA, and I have started a narrowband imaging survey in some of these dwarf irregulars focused on helium-2. It's very nice as it probes both these winds, and then if these winds are weak, which the model suggests they should be, for some of these strip stars, could probe also this ionized helium-2 in the nebular gas that should pop out quite readily. You can see our little, so we got these narrowband filters manufactured. You can see our little mandatory filter selfie there. And have started imaging some of these nearest lower metallicity dwarf irregulars, including somewhat high metallicity things, the things that are nearby. And found hints of at least a handful of what appear to be helium-2 nebulae previously unreported, suggestive of lower mass ionizers, but this is very preliminary and excited to say more about this soon. Yeah, I'll just leave my conclusions up, and thanks so much for your attention.
Okay, any questions?
This is really cool. So how did you find the initial sequel of stars? I don't know if you mentioned that, but were there prior observations?
Yeah. So that's a good question. Basically, what we've been doing, and I say we as in myself, Mode, Grace Telford has also been leading similar work. Is what you need to do basically is have HST imaging that's in at least the blue end of the optical to get a nice, somewhat crowding independent collection of blue things that are blue in the UV bands. If you want to find OB stars, basically cleanly.
So you can just go out and everything that you see as an OB star, and you just go out and see it.
That was our initial strategy, basically. Yeah. And it has, accidentally has found some of these things, partially because, you don't necessarily want to make your cut too stringent. So you're throwing out, emission line objects and stuff. But yeah, exactly. And there's not enough HST imaging is one problem. So yeah, absolutely other ways to, to either finish tiling those out, especially in the UV, or other ways to select them is very critical.
Okay, I think we're going to have to move on for time. Just feel free to find there. Thank you again. Next up, we have Karthik, who's going to tell us about constraining the types of feedback using galaxy star formation systems.
All right, wonderful. Quick callback to Sultan Hassan's talk just a few minutes earlier, where he said, let's assume that all observers are doing the right thing. I like that assumption very much. My name is Karthik Iyer. I'm a Hubble Fellow at Columbia, and I want to talk to you about stuff that we've been doing over the last year or so. This and maybe a few other things. So let's jump in. Galaxies have a lot going on, right? They are living in a large-scale environment, and that dictates sort of how gas inflows, and that dictates how much fuel they have to form stars. They have all sorts of dynamical things going on sort of at the galaxy scales, where the formation of spirals and bars and bulges affect how the galaxy evolves over time. And on really small scales, you have the formation and destruction of GMCs, where all the sorts of stuff that, again, Sultan was saying in his pressure-regulated, feedback-modulated scheme sort of come into play. And so the real challenge for almost all of us who are studying galaxy evolution tends to be the fact that the processes that regulate how stars form in galaxies tend to act over many scales, both in space and in time. And that these scales often overlap with each other and sometimes interact with each other, which means that you can't really study them in isolation. We try to anyway, but that's a separate thing. But we sort of bin a lot of this under the umbrella of feedback. And we tend to study spatially across a whole range of scales, going from like really small things like 30 Dorados to galaxy-wide or even sometimes bigger than a galaxy scales, where we look, for example, at M87's jet blowing gas out. Right? And so what I want to encourage is a temporal view of studying these processes by looking at the spectra of galaxies, which tend to contain these spectral features that are sensitive to different timescales. And so if you look at a population of galaxies across which you have these spectral features, you can start getting at what this population has been doing over time. And that gives you a complementary view of looking at feedback. So that was the plan, right? Like the plan when I wrote my Hubble proposal was pretty straightforward. It was, let's build tools that take observations and get their star formation histories. And then let's connect these using simulations that actually vary feedback to the underlying physics by saying like, how does changing the physics affect the star formation histories? And therefore, what do our observations actually tell us? This was the plan. Now, the best laid plans of mice and all of that mean that sometimes there's things that come into play that I just did not anticipate while writing this proposal. Sometimes it's observations with a telescope so sensitive that it does things that we never thought it could. Sometimes it's students that I have had the privilege of working with that just make so much progress that you're like, okay, wait, I need to keep other things aside and actually do this for a bit. And sometimes it's technical advances in adjacent fields that sort of make you think, oh, maybe I should look into that. And so I would really like to thank all the Hubble organizers for the fact that having this kind of fellowship allows me to actually spend some time looking into these things and tell you maybe a few vignettes of where these rabbit holes led me over the last year or so. So we will get to feedback, I promise. But before that, I first want to start at how we observationally constrain star formation histories. And so this goes back to this code that I spent some time packaging and now maintaining. And over the last year, I had the chance to do things like open houses where I can show people how to use this code, and it's a very rewarding experience. But the basic point of view is the fact that a star formation history is a record of how galaxies form stars over time. And many, many smart people have spent a lot of time thinking about how to describe this curve in as little numbers as possible. And so my approach to this has been to use this to essentially integrate up the star formation history and divide it into equal quantiles, and then say that these quantiles, the times when a galaxy forms certain fractions of its mass, are the parameters that I'm going to try to constrain with my observations. And so here's an example of like what happens when you sample from the space of T25, T50, T75, which is when a galaxy forms quarter, half, and 3/4 of its mass. The background curves don't show up as nicely, but the point is like just 3 numbers give you a lot of flexibility over the shape of your star formation history, even when all other things are held constant. And then if you can forward model the spectra of what these star formation histories look like, then you can always do the reverse where you take observational spectra and you do inference to get at the shape of the history. So that's been sort of the major thrust of this kind of thing. The package is now being incorporated into several other SED fitting codes like Bagpipes and PixelFit. It's available on pip, and there's a set of documentation that people can use. And the really cool thing is over the last year or so, people have been thinking about how to use this in conjunction with JWST data to do resolved or spatially resolved fitting, so you can get stellar populations across galaxies instead of just considering them as a single point. Right? And so I was spending time fitting galaxies in one of these JWST surveys that I'm a part of called Canucks, which looks at a set of massive lensing clusters, some of which were in the Hubble frontier fields. And we essentially noticed this thing that then ended up eating about 6 months of my life. But so the point is, this was one of the serendipitous discoveries that came early on with JWST. The angular resolution that JWST is capable of, combined with the fact that lensing tends to magnify these arcs, allow us to study spatially resolved objects at extremely high redshift. The thing we didn't expect was that there will be objects that tend to have these small clumps that almost look like globular clusters. And so this was originally an object called the sparkler, which we found at redshift of about 1.5. where we thought they were young star-forming clusters, but then when we did the stellar population analysis, we found that they're actually quite old. And now we actually got IFU and followed up and saw that they actually are old. So now we're trying to go to higher redshifts and see if we can find other lensing magnified objects that actually show the ongoing process of star formation rather than at lower redshifts when they're already quenched. So we were looking in this cluster, MAX 1423. And right there at the bottom corner is this really nice lens dark that when you blow up, is actually this set of, it's a small group of 3 galaxies, all at redshift 8.3, that we call the Firefly Sparkle, because apparently a cluster of fireflies is called a sparkle. So when you put the contours on top, they're not multiple images of the same object. They're actually 3 distinct galaxies, and they're all at roughly redshift 8.3-ish. And they have all been extremely magnified. So we could, through the survey, go and follow these up and get spectra, and then actually study the properties of the individual clumps that make up the system. So the primary system is made up of about 10 clumps, and we got spectra that sort of overlay a few of these clumps because it's hard to get finer than that. And they show these booming emission lines, and they allow us to sort of start characterizing what galaxy formation in this extremely magnified object looks like. So few takeaways. One is that it's extremely low metallicity. So this actually ties into Peter's talk, and I would love to sort of follow up on that more. And a few other things. When we tried to get the electron temperature from a few different methods, we found that it's extremely high electron temperatures. When we tried estimating the IMF, we found some hints that the IMF might actually be top heavy in these systems. And all of this sort of starts supporting this picture of high density star formation in these giant clumps. And so we went in and we started trying to get at the stellar populations, and we found that almost all of the mass in the system, so that's the source plane reconstruction, almost all of the mass tends to live in these compact high density clumps. So that's the star formation histories, and then these are sort of like where they sit in the density plot compared to local GCs. The really interesting thing overall about the system is the fact that compared to most of the other things that have been seen at these redshifts, this tends to be one of the lowest mass overall. And what this allows us to do is study how star formation might be occurring in a system that will evolve subsequently to be more typical of the kinds of galaxies that we see today, closer to L star, compared to the high mass galaxies that we are seeing at high redshift, which will, evolve to be much more massive over time. So this was really fun, and it sort of opened the door to creating this ladder of objects that have these compact clumps and studying what their properties are like. Switching from single objects to thousands of objects or tens of thousands of objects. This was my experience working with a student that completely blew me out of the water. Juan Alfonso started working with me as an undergrad, and he's now a grad student at Tohoku in Japan. And we were asking the question, what's the correlation between how galaxies look and how they form over time, right? This is known on large scales. There's a correlation between Sosic index and current star formation activity, for example. And we found some hints between star formation history and shape back in a 2019 paper that I wrote. But we essentially wanted to sort of quantify and codify this further and reduce dependence on like the traditional summary statistics like Sosic that we tend to use while talking about morphology and age when we talk about star formation history. So what we did was we trained a neural network to take pictures of galaxies from SDSS, run them through and predict the star formation history. Now, this worked, and it works with accuracy comparable to general SED fitting algorithms, which is very interesting because it opens the door to doing this with future observatories like LSST and Euclid, where we have a few bands but many objects, because this is both fast and it doesn't need the broad wavelength baseline that SED fitting tends to need. But the really cool thing that we did was say that, okay, we have the star formation histories. Now, can we go back, propagate the gradients through the network and ask which parts of the image did you use to make this prediction? Right? And so that formed the basis of this paper that we wrote, where this was essentially 3 years of work come to fruition. But the sort of interpretable maps that the network makes show when you consider any quantity like star formation rate or age, which parts of the image are actually responsible for driving that prediction. So in this plot, in the middle panel, red means greater flux in that area will drive up the estimate of star formation rate, and blue means greater flux in that area will drive down the estimate. So the star formation in this galaxy is driven by the clumps and not by the bulge, which is known. The really cool thing is now when we generalize that and we say, let's take all the galaxies and make these sort of maps and then start doing population level analysis, because that allows us to see how the buildup of morphological features across populations of galaxies tends to drive their physical predictions. All right. This I'm just going to tease. I might do an open mic on this, but Pathfinder was something I presented last year as a really nice way of talking to literature in a regime where literature is always expanding. So there's all these things that I said we wanted to do. And last year we had this really simple way of saying that, like, if I have a question, I take that question, I put it in context in a space of galaxy evolution papers. And then I use that to find similar papers and answer the question. In the years since, this has seen a lot of development and is now working with a corpus of about 380,000 papers to make this expanded map of all of astronomy instead of just galaxies. And that can then be contextualized and made into this visual landscape that shows all of these different areas. And the galaxy part of it that I showed last year sort of neatly fits into one small subset. But the really cool thing is you can go to pfdr.app right now and put in any question and search and get results, find relevant papers, do all sorts of things, and ask questions in different languages sometimes. All right. Camels is the original point of my talk, and this is exactly what happened to my ear. By the time I came to it, it was hard. But essentially, you can try to vary feedback, see how star formation histories change, and then use observations to constrain it. I will leave my conclusions up, and I'm really sorry for going over time.
All right, we'll take one question.
Thank you. That's generous. I thought you'd just come yank me off.
Thanks, Eric, for the full talk. The advances in star formation history modeling are super impressive. I have to ask, how do you treat the dust? Because that's just a limiting uncertainty on, there's still a big degeneracy.
Right.
On some of the stellar age stuff that you're
Absolutely.
and where would you look to?
Okay, so fantastic question. Quick answer, we treat dust as simply as almost all other SED fitting models right now. I am working to go away from this package called FSPS, which is the backbone on which dense spaces is built, to something called Synthesizer, where Chris Lovell and Ashwin Vijayan and folks have been building both more effective dust models, like what Laura Samavigo and folks have been working with, or trying to do effective dust from radiative transfer and encode that in. So like once we switch from FSPS to Synthesizer, those should be available natively for people to use. Thank you.
Okay, great. Let's thank the speaker again. Okay, next up we have Jay telling us maybe a callback to earlier this week with DEI work on emergence, telling us about how microphysics can drive the larger baryon cycle in galactic evolution.
Okay, thank you for the introduction. So I'm Jia. I'm a second-year Hubble Fellow at Princeton, but it's the first time I'm joining this symposium, so very cool to see all the talks. I'll be talking about star-forming molecular clouds and how do they relate to the baryon cycle and galaxy evolution on larger scales. So some of this work will be, so this includes work, past and current works I'm doing together with the FANGS collaboration and some ongoing and future works that I will be doing with the MOL collaboration, and I will introduce them in a second. So just to relate to some of the talks that we have seen, like back even to Monday, well, whenever we talk about like baryon cycles, this is usually the picture that we show. This appeared multiple times. So we have a galaxy in the middle, barely resolved. We have gas flowing in. Somehow something happened in the middle of a galaxy. You have star formation. You are rejecting some gas out of the galaxy. And this is sort of the zoomed out view of how galaxy evolution works. But obviously, we want to actually understand what's happening in that point of space where everything happens. And this is sort of critically related to a lot of the questions that we want to answer in astronomy. So if we zoom in a little bit into a galaxy and maybe even down into the size of individual star-forming regions, actually we are seeing a very complicated picture. There's a whole baryon life cycle on this kind of small scales on its own. So I'll step through the processes. Usually a star-forming region starts from the diffuse atomic gas, which is only visible through radio observations of the, for example, hydrogen 21 centimeter line. And some part of these diffuse atomic gas will form dense molecular gas, which will become visible in the millimeter band through CO observations. And some small dense part of those clouds will further collapse to form stars and star clusters. And once they get rid of their dust envelope, they start to show up in shorter wavelengths, including from UV to IR. And eventually some of those stars die, and they also create a lot of feedback, create chaos in their surroundings. So that will create H region supernova, stellar ejecta, that will essentially return material into the ISM to complete this cycle. And this end phase is also observable widely through observations of, for example, ionized gas lines. So this is sort of the basic idea of the baryon life cycle on the scales of individual star-forming regions, which is sort of the fundamental units of star formation in galaxies. Now, for this audience, I do want to really emphasize that this is really relevant to a lot of the fields in astronomy. So to the smaller scales, these kind of processes actually set the initial condition for the formation of the stellar and planetary systems. In the intermediate scale, they basically tell you where, for example, supernova explodes in the galaxy. And this actually has some implications on, for example, what's the feedback yield that we have heard from the first talk in this session. And on the larger scales, they basically control the speed and efficiency of galaxy buildup and also affect the enrichments of the ISM and CGM. So this is the whole range of spatial scale that this is relevant to. Now, over the past years, there has been quite a lot of progress in this field in terms of understanding all the physics that's driving this kind of baryon cycle on small scales. This is mostly through technological advancements to different wavelengths, which allows us to map individual star-forming regions across a large sample of nearby galaxies. There are multiple teams in the field that is doing this work. What I will be talking about mostly is the work that is, in the FANGS team, which I do play a lot of roles in. And just to give you a quick highlight, the FANGS multi-wavelength surveys, one of the three of the key pillars of FANGS are the FANGS ALMA survey, which targets 90 nearby galaxies with ALMA, looking at the CO transition line to look at the molecular gas distribution down to individual molecular cloud scales. In the middle, we have the FANGS Muse, which is a little bit hidden here. This includes about 20 nearby galaxies for which we have the VLT Muse IFU data. So this tells us about information for the stellar population, the H region, etc. And most recently, we have the FANGS HSC and GWST surveys, which surveys around 50 to 70 galaxies. So this gives us a very deeply resolved view of star clusters, stellar populations, the ISM traced to dust emission, and all this. So with all this kind of amazing multi-wavelength data set, we have made quite some progress in understanding how does the baryon cycle works on individual star-forming region scales. So I will briefly talk about two key questions that we are trying to address over the years among the many FANGS works. The first question is, how fast do star formation regions evolve? So this is related to like the time scale that was just appeared in the previous talk. So how do we pin down this? The idea is that very simple. You want to have observational tracers of star-forming region in different phases. And as long as you know the duration of one phase, and you compare the number counts of all the phases, you can figure out what's the duration of the other phases. I'll give you a concrete example here. This is sort of one example that people usually use. You are basically comparing tracers of cold gas, such as CO, and tracers of massive star formation, such as H alpha, and look at their spatial distribution on the scale of individual regions, which means 10 to 100 parsec scales. So you will see that in this plot, the blue is basically only CO, the gold is both overlapping, and the red is only H alpha. And you can see that they do not overlap on this kind of small scales. So what this means is that you are actually looking at individual star-forming regions in different phases of their evolution. They start from CO only, they grow, they become star forming, the stars shine in H alpha, and they will destroy their reservoir of gas. So they disappear in CO, you only see H alpha. This is sort of evolutionary sequence. And if you compare regions that are in each of those categories, they actually are quite similar in number. And since we also seen from the previous talk that the H alpha bright phase is usually quite short, about 5 to 10 mega years, this immediately tells you that the whole process should be very fast, should be on the order of 5 mega years or so. Of course, this is only one way of pinning this down. There has been other complementary efforts in trying to measure the same thing. I am particularly interested in exploring a different method, which is when you have direct detection and cross-matching of young star clusters with their massive progenitors, you can actually pin this down in a more straightforward way. So this work actually involves wonderful PhD and undergraduate students from my previous institute, McMaster University. But the basic idea is you look at HSD and GWST images, you identify star clusters. From their broadband SCD, we can basically tell what their ages are. And then you cross-match that to their immediate progenitors, which shows up, for example, in millimeter ALMA observations, for example, in CO, they also shows up in dust, they shows up in free. You can cross-match all those sources. And again, it's the same game. You count their number. And because we can measure the age of the clusters reasonably well compared to H2 regions, we can build up this whole evolutionary sequence from the beginning started sum all the way to exposed clusters, H2 regions, and exposed clusters in the end. So I don't have much time to go into all the details, but the upshot is that we confirm that this evolution, time evolution is very rapid on the scale of star clusters and individual clouds. So this, so far, we are only able to do this for a small sample of nearby galaxies, focusing on very bright regions because this is not cheap. But in the future, when we have facilities such as NGBL8, this is going to be a much widely applicable strategy. Now, this has some quite broad implications, not only in our immediate field, but also to other fields. For example, we have heard a lot of disk talks early on today. I would like to highlight that if you have gas clearing time on the order of about 5 mega years or even shorter, this actually has some implications about what are the UV radiation environment for the stars that are newly formed in a cluster, because you may have a star carrying a disk around it, and you have UV radiation from other stars hitting those disks, and that will have implications on how the disks are forming, etc. And the other thing is, if you have gas being driven away by early feedback within 3 or 4 mega years, this means that a lot of the type 2 supernova will explode in low gas column density environments. This actually means that the supernova will deposit a lot of their energy and momentum into the ISM more efficiently. That increases the yield of the supernova explosion, which is related to, again, the first talk in this session. Now, this is one question we try to address: how fast do star-forming regions evolve? And it appears that they are very fast. The second question we want to address is how efficient do these star-forming regions actually form stars? And they are called that because of a reason. And to answer this, before we answer this, I want to make some quick clarification in terms of terminology in the field. Sometimes when people talk about efficiency, star formation efficiency, what they are actually referring to is the ratio between star formation rate and the gas mass. So this is sort of the classic Kennicutt-Schmidt relation. If you divide the two axes, you get a quantity with a time unit on it. That is the depletion time. That is the time it takes to deplete gas due to star formation. And when they say efficient star formation, sometimes they mean the gas will be depleted relatively quickly. But I would argue that there's a more physically meaningful parameterization, which is if you try to compare that depletion time to the dynamical time of the system that you are interested in, here, the free fall time of the molecular cloud, the ratio of those two will give you a dimensionless quantity called the efficiency per dynamical time. So this is actually quite relevant to a lot of theoretical works, because usually in simulations, you can constrain this kind of dimensionless quantities without referring to the actual property of the system. So this can be more widely applicable. And by painstakingly trying to figure out how do we measure gas mass, how do we measure star formation rate, how do we figure out the free fall time of the cloud across the whole FANG sample, the most recent measurement of this kind of efficiency per free fall time is that this is roughly a constant number around 0.4%. So this is saying that less than 1% of gas mass is being converted into stars within the molecular cloud per free fall time. This is quite inefficient. And this is, if you combine this message with the previous one, the emerging picture here is that you have most star forming regions that live relatively fast and die young. And most of them are only able to convert a very small fraction of their gas into stars before they're dispersed by early feedback. And the buildup of the stellar population in the galaxy is only possible through their collective persistent efforts over many cycles to build the entire thing. So just like human society, large changes don't come easily. So these are the two things that we have learned over the past decades based on this kind of amazing observations with things. So the remaining question I want to mention is, how do this knowledge help us understand galaxy evolution? This is sort of the topic I will try to address over the next few years with the MOV collaboration. So MOV here stands for, well, this is an acronym that stands for Muse and ALMA, unveiling the Virgo environment, as suggested by the name. This consists of two large programs, one on VLT Muse and one on ALMA. We are targeting about 40 disk galaxies in the Virgo cluster. The reason we are interested in galaxy in the cluster is because they are on the course of falling into a cluster, and the cluster environment is doing a lot of things, try to remove the gas away from the galaxy, try to stop gas from going into the galaxy, and this is called environmental quenching. So these galaxies are on the fast track of being quenched. They are on their way to their inevitable death. And because this is a relatively fast process for clusters, this provides us an opportunity to figure out how do the small-scale process relate to large-scale long-term galaxy evolution. So for this sample, we have deliberately selected galaxies that are at different stages of the inflow. Some just falling into the cluster, some have passed the first pericenter passage, and some have been in the cluster for a long time. And by combining the Muse and ALMA observations, we're hoping to figure out when and how fast do these galaxies lose their gas and become quenched. We want to figure out whether there are any variations in the cloud population that actually make them more or less efficient in forming stars over the course. And finally, we want to constrain the multi-phase gas outflows and how much they actually influence the gas budget. This is a very, very young collaboration, and both programs are still collecting data. We have received our first bits of data over this year, and they're already revealing some surprises. For example, on the left, you are seeing a H-alpha image from Muse. You are seeing KPC scale ionized gas outflows driven by starburst in the galaxy. This is a recent inflower. So usually when people talk about cluster galaxies, they usually think about the environment does a lot of things to the galaxy. But this is saying that the galaxy itself may have this sort of outflow that can substantially impact the baryon cycle and the gas budget. On the right, you are seeing a very hot off the press ALMA image that I just imaged a few days ago. This is a beautiful disk galaxy, a little bit truncated, but you are seeing a lot of ambient diffuse gas in the galaxy. This kind of galaxy, when it's truncated, it means this has been in the cluster for long. It should have stripped a lot of the gas away. So it's kind of a puzzle why there are still a lot of diffuse gas remaining in the gas, not being stripped by room pressure. So all of these are remaining questions that we are hoping to address in the next few years. So I will leave my summary slides here and happy to address some questions.
Oh, okay. We have time for one question.
Really nice. So back to the free fall dynamical time plot that we need to talk about.
Sorry.
Do you see any or can you look for any trends in that scatter with like galaxy properties, like tumor Q or something?
Yeah. So we have looked at so basically the scatter along that relation is variation in the efficiency per vortex, right?
Yeah.
So we have tried to look for different trends. Not so much with galaxy properties, but with like local properties of the cloud population. Because from numerical simulation, we expect, for example, if you have clouds that are less bound, they should be less efficient in forming stars. So they will give you like a lower efficiency per photon. We don't see a very clear trend. The result has actually evolved over the past few years because now we have better handle on how to better measure star formation and how to figure out how to convert CO into molecular gas, which is totally a topic that I have no time to talk about, but there will be a paper coming out of it. But yeah, I think the quick answer is we have looked for it, related to the cloud population properties and haven't seen anything substantial.
Okay, great. I also have lots of questions, but let's just save them for dinner and for later. And let's thank Jay one more time. Here, so we've made it to the end of the session with our last speaker, and possibly at highest redshift. Yeah, okay, so Rohan will tell us about all the little things, which means he's definitely talking about dust. But I think he's actually talking about top 3 stars in dwarf galaxies.
Thank you so much. I do promise I will get to dust towards the end. So yeah, this is my last year at the Hubble Symposium. My name is Rohan Naidu. I'm a third-year Hubble Fellow. I'm at MIT. I want to start off by, first of all, thanking all of you, my fellow fellows. It's been a lovely time being part of the fellowship. So many great adventures have been, put together at the back rows of these auditoria while listening to these great talks one after another. And then I would also very much like to thank the leads and for all their encouragement and support and providing the kind of independence that allows one to go ahead and do pretty wild surveys like this one, which, it's unclear whether they're going to work or not at the outset, but you have the courage to do it because of the fellowship. So in this talk today, I want to tell you about all the little things. It's going to be a talk about dwarf galaxies. They're going to be lensed, and this is the last talk of a very long day. So it's going to be lots of data and just huge images to stare at. So let's start off with the first one of them. So here I'm showing you a picture of our Milky Way galaxy. It's a picture from the Gaia engine. And what's highlighted here is a bevy of these tinier objects that are on their way into the Milky Way's halo. They're coursing through the outermost regions of the Milky Way. These are all these dwarf galaxies, satellite galaxies that surround our galaxy. These are among the first systems like the LMC and SMC that told us that there are even galaxies out there beyond our Milky Way, providing us a sense for the hierarchical nature of structure in the universe, that galaxies like our Milky Way are continually assimilating these smaller galaxies. One of the key goals of JWST is to find these kind of very small dwarf galaxies at the very highest redshifts. So here I'm showing you a summary of the history of the universe. And the area of interest is these redshifts about 6-ish that were previously hidden from us prior to JWST flying. And so we'd really like to find dwarf galaxies in these early epochs because we believe they're just so incredibly numerous that they may have played a very important role in producing this enormous reionization process, where the universe then from this cold ocean of lifeless neutral hydrogen to this very hot and ionized space that we live in. So these dwarf galaxies are prophesied to be key to this process. These dwarf galaxies are supposed to hold some of the most spectacular black holes, really low mass black holes, things like intermediate mass black holes. They give you a sense of the skeleton of dark matter in the universe because they trace everything around them very precisely. So the reason we put together this survey was to do exactly this, to try and find these very low mass dwarf galaxies. This is a team comprising, over 30 members from around the world. It's led by Jörg Mate at ISTA in Austria, along with myself. This was a pretty enormous investment from JWST, about 50 hours last cycle, to get some of the deepest prism spectra we've taken till now, where we try to get spectra up to depths of about 27 hours per each object. So we decided to stare very hard at AGLE 2744, which is one of these gravitational lensing fields that Karthik Iyer was showing us earlier, because we need all our help to find these very little, very low luminosity galaxies by using the effect of gravitational magnification. So for example, I'm showing you here a redshift 4 galaxy that is magnified over 50 times. And so you can see the individual star clusters within this galaxy. If it were not magnified, it would take several hundreds of hours to detect an object that is so faint. So we are using this cluster to get all the help we can. We're also using this special mode of JWST that is pretty underrated, called GRISM spectroscopy. So what does GRISM spectroscopy do? It takes these beautiful galaxies detected in these 4 or 5 micron images, in this case, from JWST, and disperses every single pixel. So you basically get a spectrum for every single object in your field of view. So I'll just blink back and forward so you can keep your eye on this really beautiful spiral galaxy that is at a relatively low redshift. And so you see every arm of it is going to basically be dispersed, and you get this very nice spatially resolved spectrum for essentially every object in the field of view. So I've spent a good chunk of my fellowship developing tools to get the most out of these types of spectra. And one of the examples of how powerful this technique is, because you basically are able to find all kinds of rare objects without having to pre-select them in your photometry and say that, oh, this one's special, I'm going to then go and get a spectrum for it by putting a slit. You don't need to do that anymore. So you're very, very much primed to find really exciting serendipitous objects that we didn't even have the models for to select in the first place. A prime example of this is this class of objects that many of you have already asked me about this week, the little red dots. So these objects were found with the SNIRCAN prism technique, where we saw all these broad lines showing up everywhere. And then when we went and looked at their images, we found them to be these extremely compact objects that we now know to be broadline AGN, an enormous number of them, much larger than what any models had predicted. And so these types of discoveries really inspired us that we should do this dwarf galaxy search also using this, this very powerful GRISM method. But this came with lots of challenges because these kinds of gravitational lensing clusters are extremely crowded regions. So we had to come up with all kinds of technical innovations to make this work. So for example, we designed this butterfly mosaic, which got rid of many of the typical challenges in these very crowded fields. So on the right, I'm showing you examples of really challenging scenarios that have been very difficult to get spectra in. So for example, there's a galaxy at redshift close to 6 that is sitting behind this cluster member in the 82744 cluster. And yet you're able to measure a spectrum for it because of this very cool butterfly technique where we get spectra in many roles and are able to subtract out all the contamination. So you can, so I'm showing you one example there where we've done the same, where even though a star is blocking our view, even though there's contamination from all kinds of galaxies, we're able to really deconfuse this. And so the yield from the survey was pretty remarkable. So we found one of the largest samples of dwarf galaxies beyond the local group. So these are galaxies that are comparable to Draco, Carina, Fornax, galaxies that we know around the Milky Way, but out to redshifts of close to 7, where most of our sample lies. And because we're getting galaxies at every single epoch along the way, because we're getting spectra for everything in the field of view, we also have some of the deepest views of the universe, even at these relatively intermediate redshifts that were not our main target. So one of the main goals of this survey was to find extremely metal-poor and perhaps metal-free stars. Right, so this is one of the most fundamental quests of astronomy, to try and find pop-free stars, metal-free stars, some of the first generations of stars. So a few years ago, Hubble fellow Anna Schauer put out this really amazing paper where she showed that, to find the very first pop-free stars that are forming right after the Big Bang, we would need telescopes that were as enormous as 100 meters, and you would need to put them on the moon. As pictured here in the picture we took in the Kodiak day before yesterday. So there was a lot of pessimism about this particular question. But off late, when people went back and started running these very detailed hydrodynamical simulations, what they found is that there are really good chances for this very metal-free star formation to be happening all the way down to redshifts of 5, 6, 7, because what they found was that even in larger galaxies, you end up with clumps of gas that are still pristine. They might have been sitting at the outskirts of the galaxy. They might have been bumped up into their halos and formed the fountains that are falling back. They might have just been in a very inefficient star-forming region. And so you get these tiny little pockets that are still able to maintain this very primordial pristine nature. And so you can find these very late POP3 star-forming clumps. And so the key way to find these kinds of clumps is to look at these extremely magnified sources where you are able to do this kind of spatially resolved spectroscopy. So that is what is key to the search, where you really want to find these extremely metal-free pockets. So we did not find a POP3 galaxy per se, like an entire galaxy where there were no hints of any metals and only strong Balmer lines. So that's the signature we are looking for. So lines like H alpha or Lyman alpha would be extremely strong in them, but metal lines related to O3 and so on would be extremely weak. So we returned a sample of these kind of arcs. We have about a dozen such objects. Analysis is still ongoing about looking at some of these very weak clumps that might show up in that are really bright in H alpha, but are really weak at other wavelengths. So there's still work in progress, but what we can definitely report is we have these kind of spatially resolved spectra for the first time for these really, really tiny galaxies and can even begin to do this analysis. In my last few minutes, I just want to flash a bunch of things that you could do with such a large sample of dwarf galaxies at all these redshifts. Another very fundamental thing is that in these lensed objects, it's very difficult to even compute the total number of photons that are being produced when you do this slit spectroscopy, because you end up having to put your slit along one clump or another clump. But when you have this kind of fully spatially resolved spectroscopy, you actually know what the total star formation rates are in these really tiny systems, which is key to this whole business of figuring out whether they can reionize the universe or not. So this is my favorite plot that I've made with the survey till now that we're putting in the survey paper. So these are all the galaxies that we've found projected in terms of their on-sky distribution. So basically think of it as an array deck plot where the color corresponds to one of their on-sky coordinates, and here I'm showing you their redshift. And you stare at this for days, and there's so many really, really cool results in here. For example, we find dozens of these forming protoclusters at very high redshift. So these stripes of lines that you see here, these are all galaxies that are all huddled together at the exact same redshift. And so they will become the kind of systems that Michael showed us a few days ago, these really enormous clusters. You can also pick up by eye some very really interesting clumps of groups here. So this clump hosts one of the most massive little red dots that we've found till now, and it has all these galaxies clustering around it. Not only can you do these kind of large-scale environmental studies for the first time to such great detail, but you can also zoom in on really small scales. The precision of the redshift is about 60, 70 kilometers per second. So here I'm showing you one of my favorite galaxies in the entire survey. So this is a slide dedicated to all the Milky Way folks here. So this is a galaxy that I thought was a really good doppelganger of the Milky Way, which has about a stellar mass close to what we would expect of our galaxy at about a redshift 6. It's got these two tiny little satellites that resemble the Magellanic Clouds. Within about 1.5 megaparsecs, it's got all these satellites that look like fornax and so on. There's even an Andromeda-like object. But you can go and select systems like this and do this kind of satellite inventory that we've been doing in the local group and at relatively local distances out of the very highest redshifts. This is also going to be one of the best calibration fields from JWST because we've, along with our collaborators, gotten every single piece of JWST data that is possible. So every single NIRCam band, along with all these redshifts, really lets us look at galaxy properties in really exquisite detail and pull out really ancient systems like this. We can also make star formation maps that are inured to dust. So maybe Jed loves this plot a lot because we can look at tracers like Passion Alpha and Sulfur 3 that are really quite dust resistant. I'll end my talk with this sentiment that not too long ago, we were debating, very close to here, whether galaxies even exist beyond our Milky Way. And now with JWST, we are charting the very first billion years of the universe and pushing all the way to the brink of the Big Bang. And I find that, extremely, extremely cool. This is my summary, and thank you so much for listening at the end of such a long day. Appreciate it.
Okay, question. Yeah.
It's not really exactly science, but with such a large sample of redshifts and you again you mentioned alpha ratio, have you done some sort of systematic study of photoz's with JWST versus spec's at all these redshifts?
Yeah, so in this particular field, because we have such exquisite photometry, the photoz's are actually reasonably good because we have every possible piece of data you can imagine. And many of the galaxies that we detect are these emission line galaxies, which tend to boost the photometry. And so the photoz's for them are relatively easier to get, right? So if you look at how these lines are boosted here, this box of photoz's really nicely. But what you could definitely do is you can start dropping some bands, right? And then you can like ask, would this actually have gotten me this galaxy or not? So this is really the perfect data set to empirically test what kind of bands you need for your science. So if you really care about massive galaxies, you can be like, okay, I just need one there and one there to catch the break and the redshift and so on. Thanks for the question.
Okay, we're going to end it there, but let's thank the speaker again, and let's thank all the speakers for the talking. Okay, so thank you.
Sorry about that.